All right. Good morning, everybody. Thanks for joining us for the LSI Grants and Fellowships final public briefing. We have a lot of great talks for you folks today. Really excited to get a chance to share with you what our researchers are up to. Before we get started, just a couple of things. If there were to be any kind of a technical hiccup where the internet went out, we'll simply go through the process of bringing back up the loop and restarting everything. So just keep trying to dial back in. As we go through today's discussion, we will have some curated sections for Q&A where we'll be taking questions from all the folks, all the panelists, and we'll be looking for questions coming in from the webinar attendees, and we'll also be doing our best to monitor the YouTube feed. So let me go ahead and introduce a couple of folks. Let me introduce Casey Hines. She is our Executive Director at Limitless Space Institute. I don't know where she's at in your Brady Bunch display, but it's Casey Hines. Casey is our Executive Director here, and she is an award-winning educator, helping Limitless Space Institute connect with a lot of educators all over the world. And in addition to Casey, we've also got Shaka Jaliwa is here online. Shaka, if you could turn on your camera. Shaka is helping Casey with all the education stuff. He is a super smart human at all the things you can think about, from technology to engineering, and he knows how to speak to human beings. So absolutely love to have him as part of the team. Shaka, glad you are here. Let me pull up a little chart here and do a quick intro, and then I want to hand the microphone to our keynote speaker today, Andrew Duggleby from Venus Aerospace. But let me do a quick intro to LSI. So my name is Sonny White. I'm the Director of Advanced Research and Development here at Limitless Space Institute. And so most folks are aware of this, but just for the folks that are joining us maybe for the first time as part of the webinar or on YouTube, Limitless Space Institute is a nonprofit with a very unique and bold mission statement. Our mission is to inspire and educate the next generation to travel beyond our solar system and to support the research development of enabling technologies. The three pillars of LSI, we call this kind of like the inspiration circle of life, if you will. This is not the kind where, things eat each other. This is a different kind, a little bit more exciting, if you will. Inspire, educate, research. When you do amazing research, you inspire folks to go get educated. That allows them to then go through and do research, so this kind of process continues. So those are the three pillars of LSI. Our pinnacle objective is extremely audacious. We are hoping to enable real interstellar travel in some form by the turn of the century, and that is an exceedingly difficult objective and goal. But we are a doing organization. We are putting rubber on the road. We conduct research internally through our EagleWorks labs. We've been funded by DARPA Defense Science Office for a number of grants. We actually just picked up a National Science Foundation grant to continue work with some nanotechnology that we've been working on that has some power, communications, and other implications that may be of use to space exploration. We've got this amazing educator program that Casey and Shaka are doing, where they're working with educators all over the globe. It's amazing what they've been able to achieve. Trying to pull together lesson plans that are very detailed and useful to help teachers all over the globe get kiddos excited about STEM and wanting to pursue careers in STEM. And so we also have some very recent initiatives with some teachers in Nigeria and some teachers in Brazil as well. So we have some very focused things in those countries, and there'll be more to come. We also do research. We also sponsor research externally through the LSI Grants and Fellowships program, which is the subject of today. And this is where we get a chance to sponsor folks from universities all over the globe trying to do research on the frontiers of engineering and even physics itself. And so that's what we'll be talking about today. We're really excited to hear from everybody to see what they were able to achieve as part of their work. So just to kind of set the bit in terms of why this is such a hard objective, trying to get human beings, for example, past Mars in the solar system, into the outer solar system, if we wanted to get human beings to Saturn and we wanted to get them there in 200 days, let's say, the amount of energy that's necessary to make something like that possible is an order of magnitude more energy than it takes to get a payload from the surface of the Earth to low Earth orbit. So all that to say, chemical propulsion just cannot do that. And so that's why you'll see during today's talks, there's a heavy emphasis on trying to bring new solutions to bear to allow us to do this, solve this time distance problem. This is a schedule for today. We've got kind of back-to-back presentations in 20-minute TED Talk format. First up, we'll start off with a keynote from Andrew Duggleby, and then we'll get into hearing from our performers. And then we'll have can everyone see my mouse when I move it on the screen?
Hey, Sonny, I don't see your charts actually.
Well, that's, let's see here. Give me 2 seconds.
But we were gathering everything you were saying without the charts, I think.
Yep, let me try that again. Can you see my screen?
Yep, that's good now. Thanks.
Okay, all right, very good. Right, so I don't need to go over the other stuff. The pictures were secondary to my words. So this is the schedule for today. First up, we're going to have Andrew Duggleby from Venus Aerospace, and then we'll get into our performers giving their presentations. We'll have a little facilitated Q&A where we kind of consolidate the questions to a specific area, take a small break, and then we'll be in the final stretch to hear from the rest of our performers. And then that'll be the day. So let me go ahead and stop sharing. So first up, let me introduce Andrew Duggleby. Andrew Duggleby is from Venus Aerospace. He's going to come talk to us today as our keynote and tell us a little bit about Venus Aerospace and some of the work that they're doing for hypersonic vehicles and so forth. They're doing a lot of work with rotation detonation engines. Did I get that right, Andrew?
Yeah, you got it right. Absolutely.
Okay. All right. So let me hand the microphone to him. Andrew, thank you for joining us today. Looking forward to hearing your talk.
Absolutely. And I'm trying to share my screen, but it's not letting me.
Try one more time.
There we go. Fantastic. All right. Everybody see this okay?
Yes, we got you.
Right. And thanks again for having me. I know it's been a fun year over here at Venus, and so I wanted to give a couple of fun updates. The big one, we flew our supersonic drone that's shown on top. We'll show a nice video of that. Some significant progress, as Sunny mentioned, on the rotating detonation engine, the kind of highest thrust picture we have so far down on the bottom. And then I'm also going to reveal some of our testing we did in the fall and had a really major discovery that's kind of completely shifting how we're thinking about the detonation engine in application to high-speed flight. And certainly I appreciate y'all having me here as the slowest moving dreamer. I'm only talking about, hypersonics, none anything faster than that. So much appreciated for being here. So, the funny thing about hypersonics is that people tend to think that it's new. It's been a really interesting journey for us as, the use of hypersonic weapons has sort of got people talking about hypersonics, but really it's none of the hypersonics are actually quite old. And so, here was the first vehicle to go hypersonic, and it was the X-15 powered by a rocket engine, of course. And then if, space shuttle for many, many years did much faster and much higher. And so, this is really, when we think about commercial hypersonics, we're talking about not doing something new, just trying to do it more efficiently. And so I have, my favorite Enzo Ferrari quote here, which is, aerodynamics for people who can't build engines. So really, this is an engine challenge primarily, and that's how we're looking at Venus to kind of use the rotating detonation engine to change this as a big shift. Of course, hopefully everybody here has seen Top Gun Maverick. That opening scene was awesome, but it also really helped highlight some of the challenges of hypersonics. Namely, when you go fast, it gets really hot. Now, unlike the movies, if you eject at Mach 10, you don't just need a glass of water when you're done. That's a pretty harsh ejection at Mach 10. But nevertheless, that was a pretty exciting to see hypersonics kind of highlighted in movies. And so, I want to frame a little bit when we talk about engines, just as a sort of highlight, usually you're looking at, and from an air breathing point of view, a couple different configurations. So you have a turbojet engine where, the old thermodynamics, suck, squeeze, bang, blow, you're drawing in air, you're compressing it, combusting it, and then sending it out the back, and of course, extracting a little bit of work from the turbine to power that compression. In ramjet, you are using simply the forward velocity of the aircraft through compression waves to generate your compression, and then burning subsonically, and then exiting out the back. And then in scramjet, you're actually still shocking the air, but to higher pressures, but you're going to leave it supersonic, because at a certain amount of speeds, that bringing the air all the way to subsonic is crazy, crazy hot. Not only a materials challenge, but just trying to add energy once the air is already at a very hot temperature is very challenging. So I want to show you some videos of kind of some of our progress, and I'm going to kind of come back to this and then highlight what we're now thinking with the detonation engine, kind of a new discovery that we made in the fall. And so, man, all the videos played at once. Hang on. Stop, stop, stop. All right. On the top, this is our highest thrust detonation engine yet. It's about 2,000 pounds of thrust. This is jet fuel and hydrogen peroxide. And, the combustion's happening in an angular ring. In fact, this is kind of a high-speed video of what's happening. And so you have detonation waves that are standing up. Detonation is just supersonic combustion. And by doing this, we are actually, combusting closer to constant volume combustion. So you actually end up getting a pressure gain, which is helpful. If you think of a rocket plume and you look at all that thermal energy that was sort of left on the table, it was the plume was hotter on the inside of the rocket engine, but it was at higher pressure, and used through pressure, you converted some of that into thrust, but certainly not all of that energy. And so combusting with rotating detonation allows us to have a slightly higher pressure gain and then a little bit more thrust on the end. So certainly from a pure rocket point of view, detonation engines technology is very exciting, and we're happy to have really progressed it quite a lot this year. In fact, on the bottom left, this was from our fall testing, and this is now sort of a long duration. And so, big technical challenge here is that there is a lot more heat being generated through the detonations, and this is us, demonstrating that we've solved the heating, the cooling problem with the engine. So kind of a long duration run of the detonation. And then our really interesting discovery, we decided to run an experiment where we combined this with air, right? So since we were looking at hypersonic flight and not, flight into the vacuum of space, we certainly are flying the whole time, all the vehicles we're thinking about making. And so we wanted to see, could we harness the air and then with the detonation engine, mix the rocket exhaust with the air? And that was this experiment on the bottom right. And forgive the water, that was just a cheap way to keep the duct from not melting, so we can go run that experiment. And this represents about a Mach 2 condition where the detonation engine mixes with the air in a very quick amount of time. It's an old idea called rocket-based combined cycle, but it sort of stalled out with just how long the rocket plume, and any kind of rocket plume you would put in front of a ramjet was so long that it wasn't feasible from a vehicle configuration point of view. So the rotating detonation engine really changes that. And so this was an experiment we ran in the fall, and boy, it's really changing the way how we think about using the detonation engine. And so, what we're going to go try and build over the next year is certainly, we're going to build something that looks kind of like this, and where we have an aero spike on the front to do the shockwave compressions, and then we'll put our RDRE just behind that, and so that we can kind of add pressure and heat to this incoming air, and you'll see it mixed there. And that'll let us actually start the ramjet really early. So normally ramjets need to get to like Mach 3.25, maybe Mach 3.5 to start. This will allow us to start the ramjet pretty early. I'm working with a company at Cincinnati called Volantra to go do this. So this is kind of our new concept. Like I said, the kind of a major discovery for us in the fall. And honestly, this brings the timeline for flight for us way in. If you remember last year, we were talking about using the detonation engine only and kind of doing more of a boost glide formulation. This really lets us aim for kind of cruise ranges around Mach 4 to 6. And so this little video just kind of show what's happening. And so, this is from one runway to take off all the way up to Mach 4 to Mach 6. And so at first you have the detonation engine, which is providing the thrust. As you get up to altitude, the thrust will get a little bit better with the rocket plume, a little bit better expansion. And then what we're going to show here in the video is once we go supersonic, we're going to light the ramjet that's kind of behind here. And so as the shock wave stands up, we have the right amount of pressure and temperature condition to then light the ramjet. Now the ramjet's on. And then jumping forward, at Mach 2.5, we'll actually start throttling back the detonation engine. We now have enough compression from the air that the ramjet doesn't need all that much extra help. And then by about Mach 3.5, you see there, we've completely turned off the detonation engine. Since I know we have some engineers and scientists on the call, I wanted to put down kind of our modeling in terms of what does it look like from a specific impulse point of view. And so certainly this is, a way to achieve ramjet conditions. And certainly the sort of the old idea to have a reusable vehicle achieve ramjet conditions would be using a turbojet, which has its own kind of thermal problems. And there's kind of a gap there between where you can start the ramjet and where the turbojet will get you. So this is our new idea. And to kind of show where this then allows us to sit, is we are able to fly at higher altitudes. This is a plot of speed versus altitude. And I really want to highlight where, if you're trying to be a fast flying jet where you have to fly low enough to have, enough air for your jet engine as well as that ramp start, you're going to be in this kind of gray zone here where it's going to be pretty hot. And so there are companies out there trying to chase that technology stack. It's really, really hot. Whereas if you look at sort of where the SR-71 flew, and of course, range of where the X-15 flew, we have data from where this looks like. But, our idea is to fly at an altitude that's a little higher up where, titanium is good enough from a skin temperature point of view. And, but certainly enough air for our ramjet to go. So that's what we're looking at doing. And, because no one will believe your engine until it flies, we're also been on the side building drones. And this is our flight. Pause here and describe this as a supersonic drone. It's about 8 foot long. It was powered by just hydrogen peroxide thruster. So our detonation engine is using peroxide and jet fuel. So we decided to make a very simple drone with just one leg of that combustion process. And although it's capable of supersonic flight, we didn't have regulatory approval yet. So this was actually a flight where we went Mach 0.9, and that happened in February. And while we're not doing any innovations on sort of, avionics or flight controls or structures, any of that stuff, it's still a thing to go make it and do it. And so this was our sort of first drone. And so over the next year, we're going to kind of piece it all together into a larger drone that can go Mach 4 to Mach 6. And this is kind of our new configuration of what this would look like as a RDRE ramjet powered vehicle. And so something more along the lines of Mach 4, so not necessarily having to use a wave rider at those speeds. And, we are still chasing that commercial market. Of course, there are other markets before then, but this is kind of our North Star. So over the next year, what you're going to see us do is take our detonation engine, combine it with a ramjet, put it onto a new drone. It'll have a little bit larger wings than the current drone. And we're going to need to use new carrier aircraft. So, all right, we're thinking about a MiG, but there's other things that may work for that as well. So that's kind of our path over the next year is we'll fly a detonation engine on the wing of our L-29. That's the aircraft here in the middle, the black aircraft. So sort of first, flight, it'll provide some thrust, not too much. And then we'll do a drop test of the new drone vehicle by the end of the year, and then get into powered flight next year, and then on to ramjet powered flight after that. So that's our path, and glad to be here with you guys and share kind of some exciting updates on our end.
Hey, thank you, Andrew. This was great. Really appreciate that. I got just a few more minutes. I got a question that came in because I know you got to probably duck out a little bit before too long. Question just came in from Ryan Weed. He was curious about the partnership with Belantra.
Yeah.
Is there a turbo machinery path from Mach 0 to Mach 6 in the near future?
No, we're so the work we've done with Volantis so far, we did have them looking at a turbomachinery combination, and then with this new discovery of the detonation-driven portion of this, we're just going to have our detonation engine drive directly into the ramjet. The nice part there is, if you look at a full vehicle configuration, normally a jet engine might weigh about 10% of the mass of the vehicle. And so if you kind of do all the math, certainly I'm going to go back to this graph here. So certainly a turbofan would use less fuel to get up to speed, right? They've got higher specific impulse. We'll use more fuel, but boy, once we're at top speed, we don't have this big dry hulk of a mass that we have to carry. And so, in fact, we already kind of win. I'd rather take that extra 10% as fuel. We won't use nearly that much to get up to speed. And then the second part of that, and I kind of highlight a little bit here, once you're flying supersonically, the drag goes like volume squared. And so, depending how big that jet engine is, you could see vehicles that might have 20, 30% extra drag, and that really stacks up. And so, our best estimates would be that our range, if you can get rid of the jet engine entirely, that our range would go up by, 30 to 50% compared to a turbo-based combined cycle.
Okay. Yeah, very good. Do any of our performers have questions?
Yeah, this is Charles. Hey, Andrew, thanks for sharing all your great progress on detonation engines. I was just wondering about the acoustics and if is that still an issue, or how are the acoustics?
Yeah, that's a great question. When we ran this test here in the bottom right, stop. We were really surprised how quiet it was, kind of buried inside of that duct. And so, we'll take a look at it as we kind of stack up the full engine and see. But yeah, from a commercial point of view, that would be one of the limiting things. If the acoustics are still really loud, then that would be a barrier to take off. And you might find yourself back in the world of attaching a small turbine. Yeah, great question.
Yeah, do the acoustics introduce any sort of material issues or forces that you have to worry about?
No, the only, compared to a rocket engine, the interesting thing with the detonation is you actually really hear, the waves are going around about 10,000 times per second. You actually hear those overtones. So we can actually hear, you can hear, sitting in my office here, because we're just testing outside on the other side of our hangar, I can hear if we actually got to detonation or if it was just a deflagration, depending on that test. There's a whistle that shows up. That's pretty fun to hear.
Oh, cool. Thank you.
Great question from the guy that was in charge of advanced R&D at Skunkworks.
Yeah, we looked at detonation engines for a long time and tried to integrate them in, and they were never quite ready.
Yep. Yeah, that's right. Yeah, absolutely. Yeah. That was really my story, because I was at Virgin Orbit before all of this, and I saw finally the right level of progress kind of 2018, 2019 out of academia, and I said, man, here it is.
Right.
It's now getting close enough that someone should go try and raise a whole bunch of money and pull it forward. So yeah.
Yeah, and getting the turbojet up to the speed where the ramjet can take over, that's not an easy thing there, that whole
right.
Right. Yeah.
That's right. Yeah, there's a big gap there between where the turbojet sort of where it can get to and where the ramjet wants to start. Yeah.
Yep.
Absolutely.
Great solution. Really good work. Thank you.
Thanks.
Yeah, this is exciting, Andrew. We're really excited for what you guys are doing. Thank you for the update. Thank you for giving us some of your time today. So really do appreciate that. Definitely good luck in everything you do moving forward. I know you'll keep me well informed, since you and we're always doing stuff together. So
yeah, you bet. Thanks, Sonny.
That's awesome. So with that, let's switch gears and get back into grants and fellowships finale mode and start to hear from our performers. First up, we're going to have Andreas Heim, and he'll be talking to us about the work that he's doing. The title of his research is Extremely Lightweight Solar Sails for Fast Deep Space Missions. He's from the University of Luxembourg, and he's got some of his team with him today. Andreas, just as an FYI, I'll give you like a 3-minute warning just to let you know when we're kind of getting close to the end. But you have the con, sir.
Great. Can you hear me?
Yes, sir. I got you lots.
Great. Yeah, thanks a lot, Sonny, for the kind introduction, and thank you very much to the Limitless Space Institute for supporting us with this work we are going to present. LVAS is the project which deals with extremely lightweight materials for boosting the performance of solar cells. And I'm here today with my colleagues Lars Weeks and Alicia Herazimenko. What are light sails? So light sails exploit solar photons, which are reflected or absorbed by the surface and thereby exerting momentum on the sail. And typically one of the key parameters is the density of the material, which is used because the lower the density, typically the larger you can make the surface and at a reduced thickness. Now, one of the materials which has recently been developed and which has one of the lowest densities of all of the materials is air graphite. And if you look at the density of air graphite, it's actually much lower than the density of air. And it's also a very peculiar material because it has this tetrapod structure which is interconnected, interlinked, and has a kind of like spongy characteristic. So very different from traditional solar cell materials such as aluminum. The idea here is really to boost the performance, the terminal or escape velocity of solar cells, and some calculations which have previously been done show that by using air graphite, we might potentially get to other stars 10 or 100 times faster than current solar cell materials, meaning that we might get to the next stars within a few hundreds of years. Now, the objective of this project was to work towards increasing the technology readiness level of air graphite-based solar cells from Tier 1. So this is previous work that has been done on air graphite itself, but also on the proof of principle of using air graphite in a spacecraft. We have three objectives for the project. The first one was to assess the feasibility of micrometer scale air graphite structures because we want to get as thin as possible. And we had another objective to look into sail designs made out of air graphite. Because of its special characteristics, we looked into what are sail geometries that become feasible that would not be feasible with more traditional solar cell materials. And finally, we looked into feasible system architectures, meaning that, okay, you do not have the sail itself, but how do we distribute, how do you integrate different subsystems into the sail? And the objective is basically to work towards increasing the TRL to TRL 3. Now, in terms of the methods, for the first objective, we use multi-scale simulation, and my colleague Lars Weeks is going to talk about this in the following. For objective 2, we developed sail geometries, and we aim for using finite element analysis to analyze the feasibility of these geometries. And for objective 3, we used trade space exploration and concurrent engineering methods in order to come up with feasible system architectures. The team is composed of a group of senior researchers and also a group of students. Among the senior researchers today, we have, as I already mentioned, Lars and Alicia, but we also had 5 mostly master's level or graduate students involved in different work packages of the project. And with that, I'm handing over to Lars, who is going to talk about work package 1.
Can you hear me? Yeah, okay. Yes, so previously we had a couple of people who worked on it. And Erika worked on, let's say, a macro scale model where what was new to us, because I'm not I don't this was the first time that I worked on an application in outer space, let's say. So we got familiar with the inertia relief method. So how you can perform a quasi-static analysis on something that accelerates, not taking into account any vibrations that may occur. For the microstructural geometry, Anshu was involved, and Jean Ulysse on the right helped with the beam models on the microstructure. Camilo is a postdoc who helped with the macro scale part and the multi-scale part. So next slide, please. So from this is about microstructural geometry, and previously I've shown something like the left image, and there you see a periodic random strut geometry. But there are two things that we don't like about this. It is not nicely squared, and that makes it very hard to apply periodic boundary conditions. And another thing is there are really tiny struts in there that are so tiny you can't see them, and that would be a complication for a finite element analysis. So actually I spent a lot of time trying to turn this into a square, to create a square domain out of this and make sure that all tiny beams are gone. And the result of that, can you go one slide? Yes. So here you can see a typical distribution of lengths that we can get out of this such structures. And we can control that to a certain degree. And what is nice for me, at least, is that you see that there are no tiny beams. So the left tail of the distribution is gone, and that's convenient for the analysis. Next slide, please. This shows something about the isotropy. We would like to create isotropic structures, and therefore all the beams should be oriented. If you would look at all the beams together, they should be oriented nicely in a random direction. So ideally, what we would like to see here are perfectly straight lines for all the three directions, X, Y, Z. And they're not perfect, but that's because we have a finite size. So, but I'm still happy with this. And next slide, please. Yeah, what Camilo did recently is he looked at a solar sail a model for a solar sail that was not recently, but that was previously published. And we wanted to first try to capture that and then change the model, and then change the geometry, change the material from, I think they used Kapton here, and change it to to aero graphite. So here you can see that on the left you see the result that Boni published, and on the right we see a result of Camilo, and they are very similar. The reason that they are slightly different is because we wanted to use membranes instead of shells. And these type of finite elements, they don't have any out of plane stiffness. So that means that if you would start the simulation with a perfectly straight membrane, it would not work. Therefore, you have to apply some randomness, you have to apply some out of plane deformation, because otherwise there's not enough structural stability in the out of plane direction. So the difference is caused by the way we initialized that. It wasn't particularly clear how Boni did that. But if you look at the magnitudes of the out-of-plane deformations, they're very similar. So far, so good. And then on the next slide, we changed the material to aero graphite. And we started with a thickness of 1 millimeter. And on the left, you can see the vivomesis stress. On the right, you see the out-of-plane displacement. These deformations that you see, they are exaggerated, because if you would do the real deformations, you wouldn't see anything. And this looks a bit cooler. So let's go one slide further. So what we try to do here is repeat this previous simulation for aerographite and do it for different thicknesses of the solar sail. And then we looked at, in the left diagram, you see for different thicknesses, we see the maximum vormesis stress that occurs anywhere in the solar sail. And you can see that that maximum vormesis stress is very low. So one can assume that that it wouldn't fracture. On the right, you see the acceleration that is maintained because if you increase the thickness, you increase the weight. But for the realization of the solar sail that Bonnie looked at, we see that most of the weight comes from the structure that keeps the solar sail in place and not from the solar sail itself. So if you, in the right diagram, if you would change it from, I don't know, 0.1 millimeter to 1 millimeter, you hardly see a difference in the acceleration that you can obtain with this. What I don't show here is that if you make it very thin, the solar sail with aerographite, the deformations become enormous. And our model is just for small deformations. So we didn't take that into account. And that is something that we still have to look at. One slide further. Well, I don't know if I should say that. Maybe I should hand over the... Yes.
Right. Thank you, Lars.
All right.
Next, I'm going to present some results regarding work package 3, which addresses objective 3, modeling and generation of sailcraft architectures. And I'm first going to present some concepts for aerographite-based spacecrafts. And then Alicia is going to present some results regarding the trajectory and controllability of aerographite solar sails. Now, for the spacecraft architectures, we used, let's say, Strawman mission scenario, where the spacecraft is going to enter or be launched into interstellar space. We have a few mission goals. We have a kilogram-sized Strawman payload, and the spacecraft shall at least reach solar system escape velocity. And we have a generic science payload attached to the spacecraft or sail. For the concepts, we came up with 5 different concepts, stretching from rather conservative concepts to more advanced or maybe speculative concepts. The first one was a very conservative one, where we just replaced the solar sail of the Icarus sailcraft by an aerographite sail. The next one was one where we integrated the antenna for communications into the sail. So that's the reason why the sail has this peculiar shape. And the next one is a little bit more, how to say, innovative or creative. So in this sail, we repartitioned the sail or decompose the sail in order to leave space open to attach certain subsystems or payload elements, instruments into these open spaces of the sail. And also by doing that, we would somehow impact the controllability of the sail. Another concept was to use the hollow sphere and to put subsystem elements or payload elements at the center of the sail. And thereby we would facilitate controllability of the sail. And finally, we also developed a sail which has 2 stages, so two sails. A first sail which has a high reflectivity and very close to perihelion for the solar Orworth maneuver, where we approach, we get very close to the sun. We would use the reflective sail, which has a much higher temperature resistance. And then once the sail is sufficiently far away, that reflective sail would be detached and the aerographite sail would be used further. And with that, I'm going to hand over to Alicia on the controllability and trajectory aspects of graphite sails.
Thank you, Andreas. Yes, so I would like to say some words about the controllability analysis of sails, because this was some expertise that I developed while doing research in solar sails. And the thing is that the SRP force, so solar radiation force, has multiple components depending on the optical properties of the sail. So on the figure, you can see that there are mainly two components, which is the absorbed force coming from the photons which are absorbed by the surface of the sail, but also there is a reflective force, which comes from the impulse which goes to the sail because of the photons which are reflected from its surface. So the main difference is that with the reflective sail, by changing its orientation with respect to the sun, we can change the direction of the resulting force. So basically, we will be controlling the trajectory of the solar sail by changing its orientation towards the sun. The challenge with the perfectly absorptive sail is that whatever is the orientation of the sail with respect to the sun, the resulting force is always in the direction of the solar rays. So if we talk about the aerographite materials, the thing is that this material is perfectly absorptive. We don't have the reflective force. So there will be maybe some challenges or impossibility of maneuvering with a perfectly absorptive solar sail. And this analysis cannot be done just relying on the classical mathematical theories because the usual theory to study controllability of such systems relies on the such called Lie algebra run condition, and solar sail does satisfy the condition. So in order to do it, we need to find feasible trajectories with a perfectly reflective sail. And if the maneuver cannot be done with the aerographite sail, then we can propose another solution, as Andreas just presented, a double sail. So we can use a reflective sail in order to do the maneuver, to go to the sun, to use the force of solar radiation pressure, and then we will drop the reflective sail and further accelerate with the aerographite sail. So Andreas, if you can change the next slide. What I did was to propose a trajectory with starting with the reflective sail. This is a perfectly reflective sail. And what we will be doing is that we will approach the sun because the solar radiation pressure depends on the distance from the sun. And then we will use this photonic assist in order to accelerate our sail and to expel it from the solar system, basically. So here in the figure, you can see the trajectory first from the Earth orbit towards the sun in red, and then we have the acceleration trajectory in blue. It's still the elliptic orbit, and then our orbit becomes hyperbolic at some point, which is shown in the violet color. So this can also be seen with the energy plot. Andreas, next slide, please. So here you can see that the energy at some point becomes positive, which means that we have the hyperbolic orbit and we can exit the solar system. And we have two steps because 2 times we approach the sun and we will have this impulse given by the solar radiation pressure, allowing us to leave the solar system. Next slide, please. So this trajectory will of course depend on the distance from the sun. With the reflective sail, we can go closer to the sun because the material are more, be stronger again, better, more important temperature. And this is, for example, an example of a trajectory with which we don't have on the picture on the right. You can see that with the distance to the sun, which is closer, we don't have to do a second elliptic orbit in order to accelerate our sail and to access the hyperbolic orbit.
2 minutes,
next slide,
2 minutes,
please.
Alicia.
Yes. So basically, just to say what can be done further, what I would like to do is to propose the global optimal results for a trajectory for a reflective sail, because what you've been seeing is the results that we get using locally optimal control laws. And then once we have this trajectory, We can use the differential continuation technique in order to degrade optical properties of the sail, and then we will see if we can find feasible trajectories for a perfectly reflective sail. And then it will show if we can use just aerographite material for the sail, or we need to combine it with another type of propulsion.
Yeah, thank you, Alicia. Now to the conclusion and future work. So we developed a computational mechanics aerographite sail model and conducted initial simulations at a micro and macro scale. We developed aerographite sailcraft concepts with a kilogram-sized payload, some conservative designs, but also more advanced or creative designs. And finally, we initiated work on trajectory and controllability aspects of aerographite solar sails. For future work, we basically continue the work on each of these points. So further computational mechanics simulations, further trajectory and controllability analysis, and finally to converge to an integrated computational mechanics models and the sailcraft concepts. So basically analyzing the sailcraft concepts with the computational mechanics results and also the trajectory simulation in order to see what are optimal or feasible designs for the sailcraft. And there's currently a draft journal paper in preparation based on those results. And with that, yeah, let's fly to other stars, and maybe at some point aerographite might be a candidate for developing interstellar spacecraft and reaching other stars. Thank you very much for your attention.
Hey, thank you, Andreas. Thank you, Lars. Thank you, Alicia. Great job. Wonderful charts. Amazing work. Excited to continue to follow your development as you move forward. I did see a question come in to the Q&A panel. Please keep those coming. We will revisit all the questions during the facilitated Q&A after we get through these first four performers' talks. So just keep typing them and we'll log them, and when the time comes, we'll address them all. So thank you for that. So next up, we have Charles Chase from Unlab in partnership with his colleagues at Technion Israel Institute of Technology in UCLA. They're doing some amazing work on the frontiers of physics and engineering. The title of his project is Asymmetric Potential Vacuum Fluctuations, Force Experiments. So Charles, you have the con, and I'll give you the 2 or 3 minute warning when the time comes.
Okay, great. Yeah, thanks, Sonny. And yeah, thanks for the sponsorship. You can see my screen okay, I'm sure? Yep.
Yes, we got it.
Yeah, so part of the on the call is Professor Dagan from Technion, as you mentioned, and also Professor Jimjeski, UCLA. I believe he's in Croatia today. Ami is not from App Nano, who's doing some fabrication for us, is over in India and not able to join today. So our objective is to create a propellantless thrust by interfacing with vacuum fluctuations. And, you know I've presented this previously. The way that this works is we're using resonant tunneling diodes. These are structures that have a quantum well in them where you get electron tunneling. And the vacuum fluctuations will couple to the tunneling modes and will generate a force by creating a flow in those fluctuations that go in a preferential direction. And resonant tunneling diodes have been made by quite a few people. It's fairly well known how to make those things. Here's an example here. And what we're showing in this little graph up here is the probability wave and how it propagates through tunneling through the quantum well on the other side to the other side. And you can see how the probability changes as it goes through and is then out into the vacuum again. And so this change in the probability results in a force that results in a thrust. And, you know, what this enables is this idea of, you know, people talk about maneuver in space without regret. People want to fly around in space like we do in air and be able to reposition satellites. And, you know, so that's a great, very early on application. And what we're taking advantage of is that there are these fluctuations that are present, vacuum fluctuations, vibrations, change, that are always present all the time. And we're trying to control the flow and distribution of the momentum of these fluctuations. So I think a good name for this sort of propulsion is a fluctuation flow force. We're moving the fluctuations in a preferential direction by creating asymmetry. And the asymmetry is created either through a diode, you know, like I expressed, which may seem like the most straightforward way of doing this, but also it appears from breaking the symmetry of space with materials and different structures can also influence the way the distribution of these fluctuations. And so that's what we're working on. And we predict very large forces, potentially up to 9 newtons per kilogram. That's very close to being able to escape Earth's gravity. You know, what we'd build would be these diodes on a wafer, and you generate a force that way. So, you know, this is sort of an overall summary of what we're trying to do. And I won't belabor this about there's always fluctuations present, vacuum fluctuations. We've talked about this before, Jeremy and myself, you know, working on this. But if you look at quantum theory, there's one of the bases is there's a minimum amount of energy always there, as you can see over here. Uncertainty also predicts that, you know, you can only get down to a certain amount of energy and momentum. You take a look at Planck's energy distribution, the second one that he has, and there's always a vacuum fluctuation present, even when there's no thermal fluctuations. And in fact, at room temperature above 7 terahertz of frequency, the vacuum fluctuations, this component dominates over the thermal fluctuations. And then, of course, there's, you know, people talk about the Casimir force being evidence of vacuum fluctuations. You can, of course, calculate the Casimir force without using vacuum fluctuations. So it's referred to that way and pretty well accepted, but you know, it's not a proof, I would say. And so in a Casimir force, you have different fluctuations outside the plate than inside the plate, which causes a force to push the plates together. And the pressure is about 1 atmosphere for 10 nanometers of separation. And all this phenomena is attributed to vacuum fluctuations. You know, spontaneous emission, forces like the Casimir, Lamb shift, etc. Quantum chromodynamics assumes that most of a protein's mass is from vacuum fluctuations. But, you know, as I mentioned, it's a very active field of you know, unknown in a way, in that we look at the vacuum energy of free space. It's very small. QED, if you use the Planck scale cutoff, it's very large, 120 orders of magnitude different. You know, what the heck is going on there? You know, one thing I just want us to all remember is that everything is an interaction. There is nothing but interactions present. You know, and like Niels Bohr here said, isolated material particles are abstractions. There are properties being definable and observable only through their interactions with other systems. So since everything is an interaction, including the vacuum fluctuations, it's always fluctuating. There's always dynamic. It's not like there's ever a static situation. There's always fluctuations there from whatever aspect you look at that from. And so, you know, using this idea, what we've done, and this is some work from Yuval, we've taken a look at the forces that can be generated in several different ways. And so this is looking at the wave function probability using a coupled system of time-independent Schrodinger equations. And what we're doing is we're comparing a symmetric barrier structure to an asymmetric structure. And with a symmetric barrier, you look at these resonant tunneling modes. You know, here's the structure here. The resonant tunneling modes are the same on both sides, coming in and out. And this analysis was done with waves incident from both directions. And, you know, I just wanted to note that. So with the asymmetric barrier, you see where the barrier is different, the wave function is different on one side than the other. And again, this is with waves you know, going in both directions. And so we think a conservation of momentum requires that there would be a force in this situation here. And so we've taken that idea, and I won't belabor this, but using some work from Lawrence Ford, who's from Tufts University, where he's been looking at vacuum radiation pressure. You know, we've used his methodology to look at the forces. He's shown things like barrier penetration through tunneling changes with the vacuum fluctuation. You can use vacuum fluctuations to accelerate atoms. But, you know, the point is we're using his approach, and we've made some calculations of the force from a single resonant tunneling diode. And what we did is we used the experimental data from a gallium arsenide resonant tunneling diode, this one that's shown here. And we've used that to calculate what the force is on a single diode, you know, very small, about 2.3 piconewtons. But if you look at an array over a wafer, a typical wafer with a radius of 2 inches, you know, looking at the weight, you get this 9.3 newtons per kilogram of force. This is a couple of assumptions there. So further to look at the force, we've taken a look at asymmetric structures. The previous was for a diode. Here we're looking at an asymmetric structure where we have a low dielectric separated by vacuum, or even lower dielectric than a high dielectric. So 2 different dielectric materials separated apart, providing asymmetry in space. And by using pretty straightforward force calculations using Maxwell's equations, this is following along with what Lifshitz and others have done for calculating this. We predict that there will be a force present, and this is the force is plotted normalized to Casimir force. So even with an asymmetric material structure or an optical cavity, and the reason we did these materials is because we could solve this analytically and not numerically. So this is an analytical solution where you don't get into all the kind of craziness with trying to solve some of the you know, Lifshitz equations with Casimir forces. We've also done that for different metals and materials, and again, we have shown that the forces are different. This is force plotted by separation. And the forces are different depending upon the material, which kind of makes sense. But and here's the differential plotted here between 2 different materials. And so if the forces are different, we think there should be a movement there because the forces on the 2 different materials are different. And so the you know, Casimir force has been measured quite a bit. But, you know, it's only measuring attraction or repulsion forces. No one has ever measured a motive force. In other words, for example, this, you know, seminal experiment with the sphere and the plate and the attraction sphere to the plate. No one is trying to see if a structure would move or not. It's only measuring the attraction here. And this is a great summary from Jeremy's team of all the different measurements over time. But again, we're trying to measure something by building some devices that have no one has ever tried that we're aware of to measure before. And so to characterize the force, we're using a white light interferometer. And so we're building cantilevers with the structures. And so the deflection of the cantilevers would indicate a force from the fluctuation flow forces and also from gravity. And what's really nice about this approach is that you can measure not only individual cantilevers, but entire wafers so that you can measure different geometries at the same time. So we've gone to this method versus using a atomic force microscope and cantilever measurements and that, because it's will give us the data we need. The deflections that are predicted are readily measured by this, and the forces to be obtained. And Jim has done quite a bit of work. This is Paul, who's been doing some measurements for us at CNSI there at UCLA. And here's some previous work looking at cantilever resonant deflections using this approach. And so we've built some samples of this. The first samples we built are asymmetric cavities. So these are structures that have different dimensions in the cavity itself, same material. And we're comparing that to structures that have cavities that are symmetric, the same dimensions. So in this case, they're 25 nanometers each. And in this case, 10 nanometers and 40 nanometers. Build those on a cantilever. And we're making them very large, 500 microns on a side, so that we generate a large force. And building them on different length cantilevers, 500 microns, 750, 1,000, because that changes the spring constant. And so depending on the force, that would, tells you what sort of deflection, controls the sort of deflection that you would obtain. So here's some pictures of what we've fabricated. This is from Ami at App Nano. Again, different length cantilevers with the 500 micron pad here. Here's a picture of the wafer. Here's the individual ones. And here's one of the cantilevers you can see here with the 500 micron pad. Some stresses and curvature there. And here's just a picture. We use both the App Nano facility and then CNSI at UC Santa Barbara, their fab facility, to build these stuffs. And so here's some of the force data from the white light interferometer. And here you can see the picture. We measured both the asymmetric cavities and the symmetric cavities. Just a reminder of what this looks like. And so, lo and behold, kind of humorously, the symmetric, which is the blue here, deflected down, which we would expect to be in the direction of gravity, right? If there's no force, these things will weighs on the end, pushed down from, or pulled down from gravity. And then the asymmetric ones went in the opposite direction, which is what you would expect if there was a force. However, the way I say humorously, because it appears that this is dominated by stresses in the cantilever itself, because there was some plasma deposition overspray that caused some stresses here. That's so we can't declare any sort of success here. But we'll see. We're still trying to work all through that. And so we're making some new samples. We've made some new samples using atomic layer deposition. And here are the geometries of these guys that we're making. Again, the symmetric and asymmetric cavities. Here's some nice pictures of what those look like. And we've made some measurements, but we haven't, we're still in the process of analyzing that data. But these are some really nice looking samples here. And So the next steps of what we're going to do is to complete analysis of the samples that we just made, the atomic layer deposition samples. And then we need to develop an approach to flip the samples to measure the force differential. So even if there are residual stresses in the material, if we can turn these things upside down, we should be able to back out what sort of force there is, including the force of gravity and also the fluctuation flow force. So why is that hard? And I tried to put this picture here is because for the white light interferometer, we need a reference point in order to measure the deflection. And so for the one side, the one way, up here on the top, we use the top as the reference point. So the way the paddle moves relative to this reference point is easily determined. However, the way these are built, you can see they're fairly thick underneath. So to flip it upside down, we don't have a great reference point. And so there's different ways of dealing with that. And so we're working through that right now. And that would allow us to flip them and look at the differential force. And then, of course, seek funding to fabricate and test the resonant tunneling diode configurations, including, in addition to continuing this work, fabricating the resonant tunneling diode configurations, which is how this program all started, where the vacuum fluctuations couple to the tunneling going through the resonant tunneling diode, and then continuing the theoretical development that we've been doing and making sure that is ironclad. We have a couple of papers in preparation associated with that, and we'll submit those as soon as we're 100% comfortable with what our results are showing. And
2 minutes, Charles.
okay, great, thank you. And there's a way of optimizing this. So, we've talked about simple structures, but you can combine some of these ideas together. So, where you have vacuum fluctuations, you can develop a coupler that couples the fluctuations in, like you do in, here's a terahertz coupler, and centered at the resonant tunneling diode resonance. You can transport that using a terahertz waveguide, have the diode, and then add an optical cavity that would have lower vacuum fluctuation pressure and therefore tend to move things in that direction. It's interesting to think about the Casimir force and how in free space, the momentum from vacuum fluctuations adds to zero because it's the same in all directions. And that's the same inside a Casimir cavity as well. The momentum inside the cavity is zero. But the number of modes is different inside and out. And that differential in the number of modes gives you that attractive force, which is a kinetic force. And so we're just trying to control the number of modes and how they flow to achieve a different type of kinetic force than is in the Casimir force. And, so some of the applications, an initial application would be a spacecraft reaction control thruster. Again, enables this unlimited maneuverability and repositioning in altitude and inclination. You could also make an ultra stable and precise platform by addressing an array of these devices to provide very precise force. Primary propulsion, of course, if we get to the numbers we want. And then, one of Jim's brilliant ideas is a rotational configuration. You can make generators and motors, kind of like the old-fashioned toy where you have different pressure on one side than the other. If we are creating that situation, we can make something rotate. Certainly a lot of different ways of doing bearings. And this is the spacecraft I'm working on at Momentous that you can see in my background from space. Oops, sorry. And here's some of the numbers. So like thrust to weight, 9 newtons per kilogram. ISP is infinite, like a solar sail. Estimate total impulse based on lifetime is 10 to the 9th. And the thrust density, order of magnitude higher than electric. So really some great attributes, obviously, if we can get this to work. And I just wanted to end with this thought, and that, you know, sometimes a single thought can change everything. And, you know, I've always wondered about conservation of energy when a single thought, like when Mendeleev came up with the periodic table, or, you know, Michael Faraday thought about, you know, making a rotation out of a magnet, which has led to all these things. That one thought, maybe it took him 2 years to think of it, maybe it was 10 years, but our brain only uses a few calories, runs on 12 watts, you know, and how many thoughts per minute, you know, what is your interval rate? But anyway, it's interesting to think about how a single thought can change everything. And, you know, what's the conservation of energy associated with that? So I know I'm out of time, but, you know, really want to thank you, Sonny, the Limitless Space Institute, CAM, for sponsoring all this. And, you know, talked about some near-term applications if this idea actually works. But if it does actually work, we can make all these other sort of beautiful things. And I think these are from Dali, that Jim generated these for us. Like, hey, what would it look like if we had a propulsion that could do these things? Well, here it is. Anyway, thank you, everyone.
Hey, thank you, Charles. Really appreciate it. Great work. Exciting to see all the progress that you've made. Really love seeing the prototypes. I know there's going to be lots of questions when we get to the Q&A period. So again, to remind everybody, we will have a curated Q&A, so we'll save it for then. Thank you, Charles, Yuval, and Jim. I did see that Jim joined us, so good. Glad you got a chance to join us, Jim. Switching gears now, next up, we have Richard Norty from Delft University of Technology. He is not quite a new dad, but he's still kind of in that new dad zone. So if you see any kind of sleeplessness in his eyes, that could be part of the reason why. No, I'm just kidding. He's going to be talking to us about the work that he's doing with nanoscale solar sails. The title of his project is Real Acceleration and Impulse Limits of Light Sails. So with that, Richard, I'll hand the microphone over to you. Before you start, you're actually on mute. I'll give you a 2-minute warning.
Okay, great. Hey, you can see my slides normally.
We
are seeing your presentation mode, not your
Okay.
actual.
Great, thank you. I will swap. Is that better?
There we go. Perfect.
Great. Okay. Yeah, thanks for the invitation. I'm always really happy to talk at our meetings because it's just a lot of like-minded people. So it's always nice to talk here. And one of the things that we are looking at is these concept of light sails for interstellar travel. And for me, one of the really interesting thing is actually thinking about the limitations to this concept, the real physical limitations when it comes to costs, when it comes to manufacturing, because I think that these little details are also where you can actually get some very interesting physics and engineering. And so I want to talk a little bit about that. For me, when I first heard about this, is actually in the New York Times. So this is when a Starshot breakthrough was first announced, 2016. And here the idea was to launch lightweight sails that are about 1 gram with an array of high-powered lasers to about 1/5 of the speed of light. And here the idea was about using 100 gigawatts of laser power, 1 gram payload, and the idea would be to arrive at something like Alpha Centauri in a generation or 20 years. I would say one of the things that really I think motivated me was just actually some of Stephen Hawking's thoughts on this mission, and I really like it. He said, you know, I believe what makes us unique is transcending our limits. Gravity pins us down to the ground, but I just flew to America. I lost my voice, but I can still speak thanks to my voice synthesizer. And so how do we transcend our limits? And it's with our minds and our machines. And so I always found that really inspiring. And so now I kind of want to just talk a little bit about how this actually works, this whole mission. The idea being that we make a very lightweight gram scale microchip satellite, something with communication systems, power systems, radio systems. And there's a lot of teams working on miniaturizing this down to a gram. And the idea would be to attach this to large 4x4 meter-ish light sails, which are about 1 gram itself. And here, just to give you a sense, a penny is already 2.5 grams. So this is something that needs to almost necessarily needs to be on the order of hundreds of nanometers in order to constrain to these very, very stringent mass budgets. But what you find is that actually here, the idea is that it's not about exposing this for long periods of time, but it's really the idea of exposing this for somewhere on the order of tens of minutes to accelerate to the speed of light. And I think people generally are now starting to understand that pushing something stably with light over such a long time with such a high power is actually quite a complicated thing. And so now we're starting to take into account what does that mean for our manufacturing and how do we actually make these sail materials. And what makes that for us really interesting is that, if you look at the microchip, it's really about making everything smaller in X, Y, and Z, whereas the sails is really interesting challenge where you have something that's nanoscale in thickness, but really extends out in X and Y, to meter scale. So that makes it really different from any other component on this mission. And I think really very different from any type of nanotechnology that we're doing today. So just to give you a sense of kind of what we think is more or less the best sail materials that actually get you to the weight requirements that you need for these kind of laser-based light sail missions. So here the idea is that you can essentially grab a single layer of dielectric material, you can puncture it with holes, and you kind of counterintuitively make it reflective by putting all these little nanoscale holes. So this is essentially what this looks like. We usually make these on the micron scale. And the idea being that if you don't put any holes in it, this membrane, this maybe 100 nanometer membrane would be about 30% reflective. Whereas if you puncture it with holes, you can actually get it to be extremely reflective, up to 99.4% at a single wavelength. And the idea being that the light comes in, it creates a mode in the structure that you can see here, and then essentially constructively interferes with the incoming beam and destructively interferes on the other side. So you essentially get a very highly reflective mirror with one single layer, which is actually much thinner than the wavelength of the light itself. So I think that essentially this ends up being a pretty optimal material because you're essentially removing material, and in removing that material, you also make it very highly reflective. Specifically, we use silicon nitride because it's actually been kind of known in the literature to have a lot of favorable properties in terms of absorption. So this is but you can, if someone has a question on the material choice, you can ask that later. So this is essentially what these membranes look like. So here's a scanning electron microscope image that we've made. So here you can see all these little holes inside of our membrane. And if we zoom out, this is essentially the light blue part is the suspended membrane. The purple parts are where it's still attached to a silicon wafer. And you can zoom out a little bit further. So this is essentially already the thickness of a hair. And here, essentially, what you see is some of the largest photonic crystal membranes that were essentially available at the announcement of Starshot. So in 2016, kind of the biggest photonic crystals that we could make were something about 1/3 of a millimeter by 1/3 of a millimeter. And so one of the things that we've been working on now, it's been almost 8 years, is now really essentially making this much larger. So here you can see that same membrane, and we are now making these things about 16,000 times larger in area. So this is something that we've really been progressively thinking about over the years. And one very interesting thing, I think, is that if you look at these, how thin you need to make these photonic crystals to make this 1 gram target, you essentially need to make them about 50 nanometers thin. But if you were to try to get a reflectivity of 90% from something in these small mirrors, you would never be able to get this because you have to focus it so much. But when you go to these larger scales, you can actually start to approach reflectivities of 90% with this 50 nanometer thick membranes, and it's because now your sail material or your reflective material is so big that now it can actually interact with many holes and without the need of focusing it down, so you don't get all these different K vectors. So well, I think the main thing I want to say here is that there are reflectivities that you can start to achieve at these larger scales that would just not be possible at these smaller scales. So I really like this because now we're finding that, you know, with these really extreme needs that you see for missions like Starshot, you're starting to learn something about even nanophotonics. And so I want to say that one of the things we've been looking at is it's not just about making the sail lightweight. It's not just about making it reflective. It's about thinking about the practicalities of the mission. So one of the things is that right now, to make the lithography for such a structure, we've needed to do this so far with E-beam writer because the holes that you need are quite small. So this ends up being almost, for something like for this demonstrator we made, this cost is almost about 25,000 to do the lithography. But even more generally, if you look at Starshot, one of the main components of it, which is that you should be able to do a shotgun approach. You should be able to shoot as many of these as you can in order to increase the success rate. And that means that the costs are extremely crucial when you're actually fabricating these structures. And alignment resilience is crucial. And so all of these, the economics of these kind of nanotechnology is something very different than what we're used to, where we can make, you know, thousands of things on a chip, and if we have a bad yield, then we still have many usable chips. Whereas here you have really large components where yield and failure is actually at a much higher cost. And so now we're thinking, can we use these new considerations to maybe give us different lattices than what we're used to? So normally when people make photonic crystals, they're usually doing something like a square lattice or something like a hexagonal lattice. These are kind of, so this is something that student Lucas Norder in my lab has been thinking about a lot. So here again, we're thinking about the actual launch limitations. What are the things that we need to consider? So for instance, when you actually start to move these sails with a beam to very high velocities, something you have to worry about is a Doppler shift. So this is something, one of the bigger of merits that kind of takes this into account is something called the acceleration distance. So essentially, how much distance do you need to accelerate to a fifth of the speed of light? And so this includes things like the density of the sail and the payload. It also includes the reflectivity of the sail over the broad range of the Doppler shift. Considering the fact that you're going at a fifth of the speed of light. So here you start to get these betas. And so something we did was we said, okay, well, why don't we design a sail with this figure of merit, taking this into account? And we've been using a new type of machine learning combined with topology optimization. And this allows us to really look at a much larger design space than before. And so we were able to put in things like alignment resilience. And one of the things that we also were looking at is the actual feature size versus performance, which is a very interesting trade-off, because if you have smaller holes or smaller feature sizes, you can actually start to get better performance. But if they make things with bigger features, where you can use maybe flood exposure lithography, which is much cheaper, and you essentially flash a whole substrate all at once. Then this allows you to actually get much cheaper manufacturing, but at the cost of maybe the acceleration of these or the reflectance. So this is something that we wanted the machine learning algorithm to actually try to optimize. And what it comes up with is actually something very interesting. It comes up with something that looks somewhat periodic, but not really. And what we actually finally realized is that it made something that looked something like a pentagonal lattice. And you can kind of see it as the kind of two overlaid, stretched out lattices. And so this is quite interesting. This is not a type of lattice that you see in optics, at least that we've seen before. And so if you look at the acceleration distance, it starts to even above these the minimum feature size where we can start using optical lithography. It starts to compete pretty nicely with these hexagonal lattices. And so how does it do it? Well, the interesting thing is that when you think about a hexagonal lattice, what it's doing here, just like the lattice I explained before, it's having a high reflectivity at a single wavelength. Whereas what the machine learning algorithm figured out was, I don't need to have the highest reflectivity. I just need to kind of make this sort of weird pentagonal lattice that has many types of holes. And this can kind of essentially allow you to spread out the reflectance over this broad Doppler shift regime. What's really interesting is that if you look at, we started looking at things like the actual time it takes, because if you're thinking about how much laser power you need, actually time ends up being a much more important component than say the acceleration distance in some ways. And so here what we find is that we can actually, with these pentagonal lattices, we can actually accelerate the sails to a fifth of the speed of light in a much faster time than you could with a conventional photonic crystal. And so what we find is that this ends up actually coming down again to cost, because it's not just the cost of manufacturing the sail, but it's also the cost of keeping the laser on for 7 left minutes. And if you kind of start to look at what the costs are, it's something we think on the order of around $1 million reduction per launch. So these are the kind of things where if you start take into consideration some of the real kind of practical limitations, it starts to get you can start to get very interesting designs because of it, I think, and interesting physics and considerations. So now one of the things is we've now, just to show you again here, the small membranes that I showed you before, and now we can make them even larger. And we've now managed to make them 6 centimeter by 6 centimeters, so really wafer scales, single layer suspended membranes. So we really think this is essentially some of the highest aspect ratio nanophotonic structures that have really been made before. And we've done it now with about a 10,000 times reduction cost than we used to have for making these same sails. And so now this is essentially just to give you a sense of what it looks like. So here's an SEM of our pentagonal lattice. So this is a completely pentagonal lattice reflector. And we can now also measure the reflectivities of some of these a part of our reflectance spectrum to kind of confirm that these things work. One of the things that we've been looking at are actually, we still think that there's going to be some time before we make these meter scale structures. And I personally think that if you take this technology for interstellar travel and look at even things within our solar system, with the sizes that we can make today, it can actually already be very interesting. So if you look here, this is essentially some of the fastest flyby probes so far in the solar system. So here, for instance, Cassini, it took 7 years to get to Saturn. But if you start looking at just the sails that we can make today on a wafer, we can already start to essentially get these times down with a 1 gram payload. So we can get something to Mars, as fast as we can get something, as we can send international mail. So I think that for me, or sending, probes to Saturn's moons or oceans, I find that in only 22 days. So I actually find that this technology is just interesting, whether you're thinking about interstellar or even kind of at the edge of our solar system. So what we've been thinking about is whether a small scale launch is possible on Earth. And what we're thinking about is something that looks like a tether with very flexible membranes. And the idea here is to also maybe even put a frame payload made out of silicon. And so here, one of the things I wanted to say is that, the Limitless Space Institute has really been quite crucial in kind of keeping this going and allowing us to apply for more funding. So we recently got funding from the ERC. And this is allowing us to really do a first early stage tethered launches of light sails. So the idea is here that we're really combining an etcher system, which allows us to remove and suspend these structures and move them straight into a high vacuum chamber with a high powered laser. And this is going to really allow us to really do some first control flights against gravity. So you can think about it like a rocket kind of chained down and thrusters on. And the idea is also here to actually look at stability of our structures, to really see that the light sail can actually follow our laser. So this you can do by essentially slowly changing the holes as you go towards the center. And so now our students have really been working very hard, especially a student in my group named Mark has been working extremely hard on actually simulating the nonlinear mechanics of these structures when they're deformed with the laser, and then this deformation actually changes how they reflect. So it's a very complicated system, and something that we're now realizing is actually affects the stability of the structure. So here you can see some of his simulations where he's now starting to really able to simulate what these small scale sails would look like under a high powered laser and how they would stabilize themselves. And just to give you a sense that now recently this was
2 minutes.
Okay, great. Well, I think this is not working, so I'll just, oh yeah, there it is. So now essentially the system has just recently been delivered to us. So this is really quite a large system to do our first flights. And this is something that we're going to start putting into effect, in the next month. So here the idea is that, you can think about, what we're doing here is essentially optical levitation in Earth's gravity, and people have been doing this to make things remarkably isolated from ambient environments. So people have optically levitated things with 10 nanogram scales. But what we're thinking about is really starting to levitate things or really push things against gravity that are about 100 times larger than anything levitated with coherent light to date. So we're really excited about where these experiments are going to go. And this is really thinking about the optical manipulation of really much larger objects than we're used to. So I just want to say, I think we can make structures beyond what the human dexterity, and think about new engineering limits. I think by bringing together the fabrication experiments, this will really allow us to look at new, really extreme metamaterials. And I think, we have to start really bringing together our expertise now. The lasers, the laser guys and the light sail guys and the payload guys. I think it's now we're getting to the point where they're starting to have a real effect on each other because of the really stringent requirements. And I think I want to say that, when I first saw this Starshot program, I honestly thought this is just a crazy thing. We're making things that are 1/3 of a millimeter by 1/3 of a millimeter. And now in 8 years, we've increased this by, many like tens of thousands of times. But I also always like this reminder that, there's really about only 66 years between the first flight and the moon landings, so it's, you never know what's possible. So yeah. I want to thank the team here. This is a great collaboration between Brown University, also our team at Delft. Mark has been really instrumental in these simulations of sails, and Lucas has really been working on a lot of these simulations, and Atta and Vega are now really working on these levitation projects. So yeah, thank you very much, and open for questions.
Awesome. Thank you, Richard. This is great. Great stuff. We'll continue to collect the questions in the parking lot until we get to the the Q&A portion. So, but big congrats on the grant from ERC. Really glad to see that for you guys, and continue to look forward to follow your progress moving forward. So, switching gears now, we have the last talk of the morning session, and then we'll get into some Q&A. So next up we have Kirill Zatrimilov and his advisor Remo Garantini from University of Bergamo. They are definitely on the frontiers of physics, trying to figure out what some of the next chapters might be to enable rapid interstellar transit. They're doing some amazing work titled Traversable Wormholes and Warp Drive, a road to interstellar exploration. So with that, I will hand the microphone over to Kirill. And Kirill, I will give you a 2-minute warning, and I think I need to get Richard to stop sharing. Awesome.
Hi everyone. Can I start now?
Yes, please.
Okay. Okay, so the topic of my talk is warp drives, wormhole warp drives, wormholes and energy conditions. So first of all, let me. The talk is based on these 3 papers, 2 of which are 2 preprints and 1 submitted to Physics Letters B. So first of all, let me briefly go over the definition of a warp drive. So the concept of warp drives is rooted in the paradigm of general relativity. The basic idea of GR is that the presence of matter curves space-time, similarly to how when you have a rubber sheet, you put on some massive object in the middle, and then it will bend and it will affect the trajectories of other objects in it. So then basic so if space-time can curve, we can make a localized region that has the shape of a bubble that can that goes through space-time at any speed, in principle including superluminal. So the point is that unlike other means of space travel, it doesn't require any sources of energy, because the spacecraft which is inside the bubble would be moving not through space-time but with space-time. So basically space-time would expand in front of it and contract behind it, pushing it forward. However, in our universe, there is no such thing as free lunch, and in order to create this kind of contraption, we need a negative energy density. I will go into more detail on this later on. So from the mathematical point of view, warp drive is described by a metric element of this form. So more. However, we can also consider warp drives in a non-flat space-time background. So when we, so for instance, when we have a Schwarzschild black hole, it had been shown by Galfront and Payne-Levé that in a specific coordinate system, it can be written in a form which resembles a warp metric. And then we can embed an actual warp bubble in the exterior of a black hole. So now, as I've mentioned before, the problem with warp drives is energy conditions. So when we have the generically the energy condition says that when we take the stress energy tensor of the stress energy tensor of the warp drive in our case, and multiply it by some vector contracted with some vector n, then it should be greater or equal to 0. The weak energy condition states it for time-like vectors. And one specific case is the energy density. So the energy density should be positive. The other null energy condition, the vector is null. And then if we take this line element, then one can easily compute that the energy density would be manifestly negative. However, then if instead of this line element we take that one with the when the warp bubble is in the exterior of a black hole, then our energy density, while still negative, would be given by this expression. And then this expression in brackets can in principle be smaller than just v square. So if v is negative, so the warp bubble is moving towards the black hole, and the velocity is high enough, then effectively the gravitational field from the black hole would decrease the amount of negative energy density required to sustain the warp bubble. And vice versa. In the opposite case, when the velocity is directed far away from the black hole, then it can amplify the effects of a warp drive. In this sense, since the Schwarzschild metric describes not just a black hole, but any kind of gravitational point like a spherical source, it can be this finding may be useful for tabletop experiments such as the one suggested by Sonny with Casimir cavities. So if one considers Casimir a pair of Casimir plates in an external gravitational field, then it would be it would be interesting to study the resulting effects. Now, another interesting phenomenon is that if we is that the warp bubble can effectively remove the black hole horizon. Namely, if we consider the null geodesic given by an equation of this form, we see that the velocity, so this is the so for a light ray moving through the horizon, its velocity would be given by this expression. So plus is the outgoing light ray, and minus is the incoming one. And one can see that if we have just a black hole without a warp bubble, then at the radius equal to 2 gm, so the Schwarzschild radius the outgoing geodesic vanished, so everything falls inside the horizon. There is no way out. But then, if we consider this term, which has the plus sign, then effectively, when there is a warp bubble, then the observer inside that warp bubble, even after it has crossed the event horizon, the observer can send a signal to the outside. So effectively, the horizon is removed for the observers inside the bubble. And moreover, if the warp drive is going out of the black hole at a speed higher than the speed of light, then basically it's possible for the light ray to go out but not in. So there is a white hole effect. So if an observer sends the light ray inside the black hole, it would still not get in if the warp drive is going out at superluminal speed. And so one can see this. So this is the black line is the black hole horizon. You can see that in red we have the incoming geodesics, and in green we have the outgoing geodesics. And the yellow line is the observer inside the bubble sending a light ray to the exterior of the black hole. Finally, one could try to extend this scheme to Morris-Thorne wormholes. So the Morris-Thorne wormhole is a generalization of the Schwarzschild black hole given by this kind of metric. So the idea is that it glues two disconnected regions in space-time. And then one can introduce a generalization of the Galtrand-Payne-Levé coordinates here. And then once again we have something like a warp metric, but with a non-flat intrinsic metric. So then we can follow the same procedure to embed a warp drive in the exterior of a wormhole. But then, if we consider the conditions for the wormhole to be traversable, then we would get so the conditions are the flare out condition, the throat condition, and the absence of horizon. So the term in front of dt square should never become 0. And then if we can take into account both of these conditions, then effectively we would have a singularity in the resultant metric. So this function g square it's given by e to the power phi divided by square root of 1 minus b over r. And then the second condition says that the denominator should become 0 at the throat. And the third condition, horizon, says that the numerator should not become 0 at the throat. So this means that this function g in the intrinsic metric is singular at the throat. So, then we can, if we compute the Ricci scalar in this case, then we see that this is not just a coordinate singularity, but a real singularity. So the Ricci scalar has this form, and it's all the coefficients cannot be set to 0. So it means that so we arrive to a paradoxical conclusion. So warp drives can traverse black holes and wormholes with horizons, but once it encounters a humanly traversable wormhole without a horizon, then it would then it would encounter a singularity. So the singularity that throat is just a coordinate singularity for the observer, but for the warp drive would be physically real. So our conclusion is once you reach a human traversable wormhole, park your warp drive outside. Now, summarizing the key findings of our research, first of all, the external gravitational fields can affect the amount of negative energy density in a warp bubble, and so it could be useful to experiment with Casimir cavities and in a strong external gravitational field. And also, this phenomenon bears some similarities with the Schwinger effect in quantum field theory, because the Schwinger effect is when virtual particles become real in an external electromagnetic field. So basically, and here we have a very similar effect. So the amount. So the amount of negative energy density is reduced by the external gravitational field. So the warp drive, the warp bubble becomes more real somewhat. Then the second key point is that the observers in the subliminal warp drive would not perceive a horizon, so it's possible to cross the horizon in a warp bubble and then send a signal from the inside to the outside. But then the warp bubbles have a problem with humanly traversable wormholes. So this is it. Thanks for your attention.
Thank you, Kirill. As always, enjoy getting a chance to listen to your presentations. It always makes me have to kind of dust off all my tensor calculus skills and make sure I'm tracking you on everything, right? So thank you, and thank you, Remo, for that. Great talk, great presentation. I really liked your park your warp drive outside the black hole comment. That's kind of funny.
Yeah, outside the wormhole. For the black hole, you can
Yeah.
cross on the warp drive, but the wormhole, yes.
Gotcha. Very good. That's awesome. So at this point, we can go into some facilitated Q&A mode. I think we've got a couple of questions already in the Q&A box. I did get one question about the schedule for today, and I put a PDF of a schedule into a Dropbox folder and shared that in the chat. So if folks that are on the webinar want to be able to see the schedule, that's there. It should also be in the invitation as well. So, but just in case you something's disconnected or you're using a Mac versus a PC or something. So, with that, let's take a look at some of the questions here, and I have plenty on my own as well. We've got a question going back to Andreas's talk from MK Merrigan. Wondering about aerographite. Where is aerographite currently being produced?
Yeah, aerographite is currently produced in northern Germany at the University of Technology Hamburg. It's produced under lab conditions in small quantities, to my knowledge, and there are certain efforts to produce aerographite in larger quantities and make it available for industrial applications, but I'm not too familiar about the current status on that.
Okay, awesome, thank you. And then there was a question, it says anonymous attendee, so I don't have a name to give with it, but this is for folks that might be familiar, because I don't think this was in anybody's talk per se, but you know, Breakthrough Starshot's shotgun approach to solar sails to send numerous ones. Has there ever been any talk about the success percentage in terms of that, or was that just a philosophical thing that they rolled out?
Maybe I can. So I think it seems to be at this point. I mean, just making one is already a big challenge. I don't think it's gone so far as to talk about real yield yet, because even just making a sail would be just really decades away, I think. So it's I think it's hard to say at this moment.
Right. So nothing in the literature speaking to any probabilities, because we have a number of other problems we need to solve first.
I think so. I think before you realistically talk about these things, I think it's going to be so integrated with how you integrate chips onto it. How do you, some people are thinking about needing to spin these sails to get them taut and stable. I think there's a lot of challenges with that too. So it seems like there's really a lot of requirements, and we're gonna have to figure out what that midway is, that midway kind of solution is for everyone.
Awesome. I think I'll open it up to all the panelists to ask some questions of the 4 talks we had this morning. Has anyone got any questions they've been kind of holding in the hopper they wanted to go back and throw into the sandbox? I will take chairman's prerogative here, and I'll throw a couple questions out there. So Andreas, in terms of the trying to realize a sail based on this aerographite, in all the work that you've done so far, do you have an idea in terms of what the upper limits might be for a aerographite sail without a ground station, right? In other words, no beaming, you're just using solar flux, right, to be able to accomplish the mission based on, like, the next 20 years, let's say. What do you think could be an achievable velocity? And we won't hold you to that.
Yeah, it's a great question, and for the time being, we do not have a precise answer or precise range, for the simple reason that there are certain effects which are probably going to impact the mechanical stability of the sail quite significantly, and one of them is thermal effects, because aerographite seems to have a fairly limited temperature range, which goes up to, I think, around 600 degrees Celsius, which is lower than some of the dielectric materials, etc. Which means that we cannot really go that close to the sun.
Okay.
And that's probably going to be the limiting factor. Nevertheless, if you would release an aerographite sail in Earth orbit, you would already have a sufficient velocity for solar system exits. So that's probably something that could be done in the next maybe 5 to 10 years, given that aerographite is available in larger quantities, and it does not reach the temperature limit.
But if I could extend on that, in your mind, in the next 10 years, how big of a sail would you hazard to guess we could potentially hope for with aerographite?
Yeah, I would, and this is just guessing. So a aerographite sail of a few square meters, that's probably something that could be done. Depends on the manufacturing facility, because you would use like a vacuum chamber in which you would deposit the graphite, and the limitation is probably on what kind of production equipment can you put into a vacuum chamber? So maybe you could roll up the material and then have like a continuous manufacturing process. But in that case, the sail would have probably a little bit of a peculiar shape. So yeah, size-wise, I would say square meters. That might be something feasible with existing vacuum chambers, easily accessible vacuum chambers.
Awesome. Great answer. Yeah, thank you, Andres. Anyone think of any questions before I continue with my chairman's prerogative here?
Maybe I had a question actually for Andreas. I was actually just kind of based on a little bit what Sunny was asking, but what is the black body radiation like? What does the emissivity look like on these aerogels? Because I assume that it has a lot of surface area, so it's probably actually very good at radiating heat. Is that a known thing or?
So I don't know the values from the top of my head, but there's a paper written among others by Martin Teimer from TU Dresden, and they used, I think, a laser in a vacuum chamber to heat up aerographite, and I can provide you with a link to the paper, and I think in that paper there's some certain properties of the aerographite under laser impingement, basically.
Yeah, thanks.
All right, I'll take Chairman's prerogative again. I have a question for Charles. Charles and gentlemen, you all, right? When I looked at you showed the results of the little cantilevers that you guys had managed to make, right? And you were showing the difference in the steady state deflection of the devices, and kind of baked into, I'm anticipating the philosophy is you have your nulls kind of baked into alongside your ones that have the asymmetric resonant tunneling diodes. So you can kind of compare and contrast the response of the system. And I love using the ellipsometry approach. Genius, absolutely genius there. But in my mind, I mean, I get your qualification saying that you anticipate there was a lot of stresses, residual stresses in the cantilever. So this is, confounding signals that prevent you from being able to see it. But I think the question is, there's a stark difference between the RTDs and the nulls, right, if you will. And so, I mean, the fact was there variation in the difference between the two? Because I get the fact there could be residual stresses, but in my mind, the residual stresses would probably be, I would have thought would have been similar. But maybe I misunderstood what you were saying with that.
Yeah, so all the samples behave very similarly. You know, the symmetric and the asymmetric, they all bent in the same direction.
Mhm.
Those were made on different wafers, and the processing was slightly different between the two.
Mhm.
And so we think there's more overspray associated with the asymmetric ones.
Mhm.
So that was one of the reasons we went to the ALD, the atomic layer deposition, is to ensure that the processing is 100% consistent across the different samples. So, we think there might be a processing difference between the asymmetric and the symmetric ones that could be causing the the apparent, if it wasn't for that, we'd be like, jumping up and down.
No, I gotcha.
Yeah.
And so you guys have the ALD equipment at your facilities at UCLA, Charles?
At the UC Santa Barbara CNSI. And so those have been made already. And I showed some pictures of those. And Paul made some preliminary measurements. He's actually moving to Zurich, though, for a job. And so the analysis of that data is not quite done yet. It should be done in the next week or two, and we'll see how that turns out. I don't know, Jim, is there anything else you wanted to say about that?
You're muted.
Oh, you're on.
Hi.
Yeah.
Yeah, I'm here. Yeah. No, I think the ALD is the way to go, and the plasma method had the problem that when the cantilever is near the substrate, because we're doing the plasma from the top, then you can get some plasma underneath. We never anticipated that, and we never anticipated that the different parts of the cantilever array would be different. But essentially, you know, the idea is that over the whole wafer, we can have multiple types of structures, you know, different asymmetric structures with different thicknesses, and really the best results will be obtained when we can turn the wafer upside down, because then we will be looking at the difference between the effect of gravity and the effect of the you know, the vacuum fluctuations, and that involves some changes to the wafer design. It's just a matter of, you know, micro fabrication. And, you know, you probably know, Sonny, you know, you run into all sorts of problems when you try to, you know, make these micromechanical structures.
Yes.
But they can be overcome.
Okay. Awesome. Yeah. Thanks. Thanks for that. Appreciate that. Look forward to kind of seeing a nice little delta from you guys in the coming week. So, what other questions have we got from some of the panelists?
Actually, I have a quick question. I don't know if anybody has been watching the three-body problem. It's a Netflix series, okay? And in the end, they have to send a spaceship, you know, to try to reach these aliens. And I must say, the ideas I've heard so far today are much better than the idea they come up with in the Netflix series. Anyway, that's all.
I agree. I watched the stuff in the Netflix series and I was like, wow, okay. All right. There you go. So definitely kudos to you guys. You guys are you're setting the bar high. So if anyone from Netflix ever happens to stumble across this YouTube, come on, pick any of these folks here. They can help you out. So, what other kind of questions or comments we got from folks?
Yeah, I mean, this is not a question, but just a comment. I once consulted for Disney Animation on a project they had along similar lines. You know, they really wanted it to be realistic yet far out. It was a lot of fun. Project went pretty far along and they canceled the darn thing.
Oh no.
They pulled the plug. I don't know why, you know, but yeah.
Yeah. I served as a consultant on the movie Tomorrowland. Where they were making some of the movie dependent upon higher dimensional physics, and so I served as a consultant on that. And then there was
nice.
Yeah, so that was interesting. Of course, my name was not in the credits. It was the NASA PAO person whose name was in it. So
right.
You got to do right. So. Anything else? Well, let's maybe we can take this opportunity to try and get just a little bit back on schedule. We're about 7 minutes over, so not too bad. We were supposed to be taking a break at 12:10, it's 12:17. So we'll go ahead and plan on taking a break at 12:20, and then we will get back. Instead of starting at 12:30, let's start at, and these are central times, central daylight time. So 20 minutes from now, let's plan on getting back together. And then we will hear from Jeremy Mundy from University of California, Davis, to talk about his work. So I'm going to go ahead and put up a little slide that lets folks online know that we'll be back at 12:40 CDT, and we'll finish up listening to some more awesome talks from the rest of the performers. So with that, thanks everybody for online that's listening to us, and for the folks that are in the webinar, we're just going to pause everything in place. You want to go grab something to eat or whatever, feel free to do that. And so all of the performers, if you would, turn cameras off and make sure you're on mute. So we'll be right back, guys.
Okay, so I just joined.
Yeah, great. folks that are watching on the webinar or YouTube, we're just kind of getting back here from a little 20-minute break. We'll be getting started here in just a minute or two. So that's why you kind of saw a little bit of a pause there for a second. So. And Phil, I believe I saw you join. You still there?
Sorry, you're talking to me, Sonny, Philip Lubin?
Yeah, just confirming that you're still there.
Yeah. Yeah.
Okay. Awesome.
Can I show you a full screen just to verify that you see it not as a double?
Yeah, please.
Okay.
I see it in the normal PowerPoint editor mode.
Okay.
Now I see it as that secondary thing.
So I guess this question is, sounds like you don't see it. Hang on.
When you go into that mode, so you click show, right? And I think if you look where it says display settings at the top, there's a little caret right beside display settings, the very top ribbon.
Okay.
So this is in where I can see, phased array program overview. I can see executive summary.
But you see two slides, not one?
I see two slides, but if you go to the top ribbon above those two slides, go to the left and you click display settings.
I got it.
And I think you can swap present view and slideshow. And then now we see just the slide. I actually learned this today watching one of the other performers give their presentation. They did that right in front of me. I was like, aha. So came in handy. Very good. Right.
Okay. All right. So I'll cut this now. Great. Okay. Thanks.
Okay. Thank you, Phil. All right. So it's 12:40. Let's go ahead and get back started. Thank you, everybody, for sticking with us so far. We are about to go into the afternoon session. We've got coming up here, Jeremy Mundy from University of California, Davis is going to be talking to us, getting back into the quantum vacuum again. And he'll be talking to us about some work he's doing, studying the Casimir force. And his project is titled the Casimir torque thruster. So with that, Jeremy, I will hand the microphone to you, and I will give you kind of a 2-minute warning just to let you know when we're getting close to the end.
All right, sounds good. Thank you, Sonny.
Thank you.
All right, so it's a pleasure to be here. I assume everybody can see my screen okay?
Yes, we got you.
Okay, great. All right, so I'll be talking about our seedling project called the Casimir torque thruster. And so let me give you a little bit of a background on this and then get into the details more. So first off, this concept involves three different concepts kind of being merged together. So the first is the Casimir effect. Next is Casimir torque. And last is the dynamic Casimir effect. And so I'll talk about all three of these very briefly, basically like one slide each, and show how when we put these concepts together, we have a mechanism for driving a torque that can then be used as a thrust through the generation of photons. So first, I'll briefly mention the Casimir effect. So Charles talked earlier about quantum fluctuations in the vacuum and had mentioned that one of the consequences is something called the Casimir effect. And so kind of briefly in one slide, I'll describe how that works. So the idea is that you have these quantum fluctuations. So these are fluctuations of electromagnetic fields. And as such, if you were to constrain the boundaries on these fluctuations by putting metallic plates that cause the fields to go to zero at surfaces, you can find which modes are allowed to fit inside this cavity. And so you can sum up the energies associated with that configuration. You can also sum up the modes that you'd have when you bring the plates closer together. And obviously, when they're closer together, you can't fit as many modes. These long wavelength modes will no longer fit inside that cavity. And so you can look at the energy difference between those two, and you'll find that there is an energy difference, and that it goes as 1 over the distance between those plates to the third power, and also scales with the surface area of those plates. And so this is the potential energy configuration associated with these two parallel plates. And so because this potential energy does vary with distance, you can look at the force that would exist by taking minus the derivative of this potential energy. And so you find that there's a force between these two plates. There's a minus sign here, which denotes that it's an attractive force. There's fundamental constants here. We have a 1 over d to the 4th power, so it's scales very strongly with inverse 4th power of the distance, and again scales with the surface area. And so this is the phenomena that Casimir had predicted back in 1948, and it has since been given his name, the Casimir force. And over the subsequent decades, there have been a number of experiments that have confirmed the existence of this force. So this is the Casimir force. So rather than having two ideal metal plates that force the fields to go to zero, what would happen if you had anisotropic plates? Or any sort of material that's anisotropic. So it could be, for example, a birefringent plate where the index of refraction depends on the orientation of the electric field compared to the surface. Or it could be a rod or something like that. But anyway, something that has some sort of optical anisotropy. And so for the example of birefringent plates shown here, in the top, when they are aligned, you have some amount of field confinement based on what the index of refractions are for the different polarizations that are incident on the plate. And if you were to rotate those plates, then you would change those boundary conditions. You would change the confinement of those modes. And so what that means now is that the mode density here depends on the angle that you have there. And so if the vacuum energy then between those plates depends on the angle, and thus you would have a torque. And this was developed independently by Persegian and Wess, as well as Yuri Barash, kind of in the 1970s. And so this is another interesting concept based on quantum vacuum fluctuations that was then experimentally measured a few decades later. And so the final component that I wanted to bring in here is something called the dynamic Casimir effect. And so you can think of this as the generation of photons by motion involving basically a changing boundary condition. And there's this nice little cartoon that I think gives you a good description of kind of what's happening here. So imagine you have an empty box, right? But we live in the quantum world, and so there's actually quantum fluctuations. But anyway, we'll assume it's basically empty, but there are still quantum fluctuations. So you close this box and you shake it up, and when you open the box, you find that light comes out of it. And so this is a consequence of rapidly changing boundary conditions that are imposed on quantum fluctuations. And so this idea goes back again to the kind of the 1970s. And looking at basically if you have a boundary condition that can move rapidly, then you can promote vacuum fluctuations into real photons that are potentially measurable. And so for the situation of just a mirror that can oscillate back and forth, you can find that this number of photons kind of scales as the frequency of oscillation and the maximum velocity squared. And so this has also been observed, again, kind of several decades after the original predictions. In the experiments that have been performed with these sorts of systems, they haven't actually been physical mirrors that have been moving, but it's usually something else that changes the boundary condition. So you can imagine if you had a material where you could change the index of refraction rapidly, that would effectively be a rapidly changing boundary condition that could then be used to generate photons. All right, so with those three ingredients, the Casimir effect, the Casimir torque, and the dynamic Casimir effect, we were starting to wonder about what would happen if you had an anisotropic disk or a particle like a rod or something like that, and you were to rotate that rapidly. What would happen? And so conceptually, you could imagine you have this object that rotates. You have these rotating boundary conditions that would then allow for photons to be emitted. And so when we were first, so if you have the photons being emitted in one direction by conservation of momentum, then you could then push the object in the other direction. So that would give you a form of propulsion that we're calling this Casimir torque thruster. And so we initially started off with kind of a back of the envelope calculation to see, what this would look like. And so if we start off with the expression that we have for an oscillating plate, just a plate moving up and down, that again, it goes as the frequency of oscillation and then the max velocity squared. And so again, that's worked out for a plate. And we said, well, what if that oscillation frequency were actually like a rotational frequency, kind of order of magnitude? Do these things, what would that give you? And so we would then take the velocity, be the in velocity of some sort of disk, and that gives you this photon generation rate that goes as the square of the radius, the cube power of the angular frequency. And so if you had a disk that was about 20 microns and an angular rotation speed of kind of gigahertz, then you would generate kind of 40,000 photons over the course of about 24 hours. So again, kind of very rough, crude approximations, but we thought, well, this at least seems kind of interesting. Is this realistic, and could we actually calculate some sort of anisotropic object rotating and see what kind of photon generation we could get? So that was kind of the purpose of the seed grant, was to theoretically investigate that to see, is there anything there to look into? And so we started off with this kind of ballpark calculation that I'd mentioned, saying, well, okay, maybe this is interesting to look at. And so then we began a couple different approaches to try to calculate this more exactly. And so the two approaches we looked at, one is a dipole approximation approach, which I'll talk to you a little bit more about in the upcoming slides. The other one is a scattering matrix approach. And so we pursued both of these early on during the first phase of the project. And we found that the numerical scattering method was very time intensive computationally. And there's still some potential there. And it's interesting because you can go to a lot of more complex geometries, but at the same time, we found that the dipole approximation actually gives some really nice sort of analytical results that is easily expandable as well for some special cases of small particles. And so that's the one that we ended up focusing on. So that's what we looked at and have been focused on for the last 6 months or so. So I'll talk about the results we have on the photon emission that we have for this Casimir thruster based on dipole approximation of a nanostructure rotating. And then I'll also briefly, if there's time, talk about a kind of related investigation that we did when we started thinking about these rotating objects that we could use the Casimir torque in order to create acceleration from the disk by basically having a linear motion that could then be converted into a rotational motion that we could then use to accelerate something. So I'll tell you a little bit about that as well. So first starting off, looking at the existing theory for kind of dynamic types of Casimir effects where you would have a rotating object, we found that there weren't too many papers that would go into much detail of this. And so there's some nice work here by Bob Jaffe and Miran Kardar at MIT looking at spontaneous emission for rotating objects. Which sounds quite similar to the type of thing that we're looking at, but it turns out that they're looking at a system that they do a lot of analytical work. They get some nice expressions for objects that are basically rotating around the axis of symmetry, which is the opposite of what we want. So you can imagine like if you had a rod and then you're just rotating the rod in this direction rather than in this direction. So it was the approach is one that we could use, but it turns out that it actually gets much more complicated when you try to switch to other geometries. And in fact, they had looked at this approach as well, scattering approach, to try to generalize it to other sorts of geometries. And they could do that, but they could only do that with scalar fields, or at least they only had done it so far with scalar fields. And so we want this for electromagnetic waves, and so we need vector fields. And so while some of the behavior is kind of qualitatively similar, it's hard to get kind of real world numbers out of that sort of theory. And another body of work comes over here about looking at rotating particles and the concept of vacuum friction. And so here, if you have a spherical object that's rotating, if you bring it near a plate, there will be a vacuum friction that will cause that plate to, or the sphere to slow down its rotation. And so this, again, has some similar sort of elements but it's not really related to emission here. It's more about the friction. And so what we did is we have our collaborators here, Paulo Neto and one of his students at the Federal University in Rio de Janeiro, Brazil, who I've been talking with for a number of years about different dynamic Casimir effects. And we were chatting about this and came up with he came up with the idea of looking at the dipole limit of such a structure, basically of like a rod. And so the idea here is that you can approximate some sort of nanoparticle that's rotating along the perpendicular axis. And that's pretty much what we want to do. And so in the dipole limit, what we want to have, so this is the same sort of dipole limit you have in classical electromagnetism or looking at quantum systems as well. And basically, you want the emission wavelength here to be large compared to the particle size. And in this dipole limit, you're basically treating whatever this nanostructure is as a dipole. And so the actual geometry of it doesnn really matter. So it could be a rod, or it could be some other sort of oblong shape, something like that. And one of the reasons they were interested in that particular geometry was because there was an experiment a few years back by a group in Purdue that looked at this optically levitated nanorotor. And so that's what this experiment looks like. So what they were doing is they had either a single nanoparticle or what they would call like a nanorotor. And it's basically two particles that are linked together here, kind of like a dumbbell. And they would then put that into an optical trap, and then they could rotate that optical trap. And so then they could get these nanoparticles to rotate at relatively high velocities. And so for this structure, these were 150 nanometer radius particles, and they were getting kind of gigahertz frequencies of oscillation here. So here's some of the experimental data that they had looking at both these nano dumbbells and nanospheres, again, getting kind of gigahertz rates of oscillation here. And so the question was, they weren't looking for dynamic Casimir effects or the generation of photons, but in principle, you could have that occurring here, but there's not really any theory that has been developed for that sort of geometry. And so what Paulo and his students did is they looked at what this generation rate would actually be for this nano dumbbell configuration, and found a relatively straightforward expression here. And so this is, again, in the dipole limit. The optical properties are that of an ideal metal. And this is the sort of expression you get out, which is it's a pretty nice expression because you have just some fundamental constants in the front here. So it's the Raman zeta function here, which is about 1.2 is the value of that. So just some other constants here. Then in the ratios here, we have R being the radius. We have the omega being the angular frequency. C is the speed of light. This is all to the 6th power. And then we have the angular frequency here again. And so we're excited to take a look to see what the kind of values you might get out of that. And if you plug in the experimental configurations from the Purdue group, you find that the generation rate, so this would be the number of photons per second, is very, very, very small, 10 to the minus 19. So conceptually, it's interesting to think about, but actually measuring this sort of photon rate, you have to wait a very, very long time for any photons to be generated. So at first we were thinking, okay, this is not good news for the Casimir torque thruster, but let's dive a little bit deeper into this and see what else we can learn. So a few observations about this. So first, the rate goes as the 6th power of the edge speed. So like if you have the edge of this dipole going around, you can relate that to the angular frequency and the radius here. So it scales as omega r. And so since it goes to the 6th power, you'd like to increase that speed as much as possible. The rate also goes linearly with the rotational angular frequency. So looking at this equation, so we can see that the product of those two goes with the 6th power, but then it also goes linearly with the radius here, because the product of omega and r, like I said, that's kind of like a speed. So you can kind of think about this in terms of speed or angular frequency. But because the angular frequency, there's basically 7 of those, there's only 6 of the r's, if you want to, you'd be better off increasing the omega rather than increasing R, right? So if you want to get the highest sort of speed possible, really what you want is you want a high angular velocity and a relatively small R by comparison. So those are ways we can think about trying to improve this. And the other point is that this rate is for a single nanoparticle. And so if you're thinking about this for some sort of thrust application, you could be thinking about an individual, nano thruster, or you could think about making an array of such thrusters and have a larger surface area, which would probably be the route that you'd really want to go on that. Okay, so then we said, well, what are kind of the fundamental limits that we could have on such a phenomenon now that we know how to describe it? Well, in terms of this dipole approximation, it's valid as long as R is still large enough that we can consider Maxwell's equations macroscopically. So once you go down below, say, a nanometer, then you start to resolve kind of atomistic properties of matter. So that would be kind of too far. So maybe in the limit, you can go down as small as about one nanometer. Speed, how fast could this be rotated? Well, the maximum speed limit would be c. So we could get a limit there, saying maybe we want to be some fraction of the speed of light, maybe 1% or 10% or something like that, to give you kind of a max speed that you could operate at. And so just rewriting that expression, we can rewrite that in terms of the fraction of the speed of light here. So that's what C0 is. It's basically our velocity at the edge of that dipole divided by c. So that's what we call C0. And then our radius is here as well. So now with this expression, we can plot a few different values and kind of see what that looks like. And so what we have here is the emission rate, so photons per second, as a function of the fraction of the speed of light, going from 1% up to 10% for different radii. And so we've limited ourselves to 1 nanometer being the smallest radii, which is right there. And so you can see now that by increasing the rate of the rotation here to being, say, 1% of the speed of light, we've dramatically increased the potential rate of photon generation. Before it was 10 to the minus 19, and now we can be up closer to, say, 10 to the minus 4, or even more if you are willing to go up to, say, 10% of the speed of light.
2 minutes.
So we found this very, very intriguing. So the next, sorry, was there a comment?
I was going to say 2 minutes.
Okay, 2 minutes. All right, great. Thanks. I'll speed up here. So then we could also look at this per unit area. If you look at it per unit area, obviously it's a very small particle, and so you can imagine having a lot of them over this over some surface. And so in this case, we can really get up to very, very high rates here. And for a comparison, if you think about the number of photons from the sun that are hitting the Earth per meter squared, it's about 10 to the 21. And so we're kind of that order of magnitude here with these structures as well. So this is a tiny rotating object that could have a photon density comparable to the sun's at the Earth's position. So next steps, we're incorporating other sorts of realistic optical properties. Right now, they're ideal metals. The other thing is we've bounded ourselves by the speed of light, but we could also further bound ourselves by saying, well, how strong can these materials be without actually breaking apart, and things like that. So I think for the sake of time, I'll say this is kind of the significant result here that we're really interested in, and seeing that it does appear that such a Casimir torque thruster is an interesting option for generating photons. And I'll skip this part about torque acceleration. I'm happy to talk to people about that if they're interested. But basically, the idea is that if we have two plates that are anisotropic, we can actually oscillate one relative to the other. And if you get the timing of the oscillation right, you can start to make it so that one plate will rotate continuously. And then over the course of several seconds, you can again get up to rotation rates that are kind of on the order of 10 to the third. So pretty fast rotations over just a few seconds. So with that, I'd like to just thank the Limitless Space Institute for making this possible. It's been a lot of fun working on this project, and thank Sunny for having us present here today.
Thank you, Jeremy. Appreciate it. And thank you for suffering through your allergies. I know you're
thanks.
struggling with that. You did great, man. You did great. We were tracking you great. So good work. Congratulations on all your hard work, and neat to see the collaboration with our friends down in Brazil. So if folks have questions, just as a reminder, we'll do some facilitated Q&A at the end of everybody's 20-minute talks. Next up, we have Phil Lubin from the University of California, Santa Barbara, where the weather is always awesome, and I'm very jealous. But he'll be talking to us about beamed energy propulsion. The title of his project is The Path Forward, Directed Energy Phased Array Technology. So with that, Phil, you have the con, and I will give you kind of like a 2-minute chime when the time comes.
Okay, can you see it full screen?
Yes, we got it full screen, bud.
Okay, great. All right, so I'll give you an overview of where we are with so this long-term vision of how one might accomplish that which is very, very difficult currently, namely to go very fast compared to chemistry. I'll give you kind of an overview both of our vision as well as where we are technologically. We've done quite a bit of building of things. Anyway, the basic idea is that if you can project power in the form of photons, so such systems are normally referred to as directed energy systems or beam power systems, depending on which side of the fence you're on. It's scalable, unlike many people who think that we're just sending little wafers to other star systems. That's not what the program is. It is a scalable technology that allows you to do things such as sending fast solar system missions, like people to Mars, large missions, high mass missions, via what we call indirect conversion, so directed energy, reconvert on board the spacecraft, and then drive high specific impulsed ion engines. So we did a study for NASA showing that you could get humans to Mars and land them in about 1 month. The other end of the spectrum is the direct drive, which is photon momentum transfer, which does allow small relativistic robotic probes to exit our solar system. But we often get stereotyped into a box. It's mostly my fault, but this is a program which allows things that have many, many different exit points. I'll give you a quick overview of our phased array program, deliverables, where we are, and then progress and next steps. Okay. All right. So from an artistic point of view, this is what it might look like. You have a source of light, which for us is a phased array laser system. You would start on the Earth, but that's not really where you want to be. You want to be on the moon or somewhere in space because the atmospheric perturbations are pretty formidable. But I'll show you that we have a way to deal with that, but that the Earth is not the right place for this in the long run. The upper one shows a directed energy reconversion on board to electrical power, then driving an ion engine. And so going to say Mars. In this case, when you want to slow down, you flip the ion engine so it's going the other way and you slow down. So from the same photon source, you can drive a probe outward, in this case, perhaps a human mission. And then you can flip it around and then slow down. So we have a paper, Sheeran et al., which you can find on our website, that discusses a variety of missions, including 100-ton missions out to Mars. The lower one is the direct drive, where photons transfer the momentum to a mirror, and the mirror is projected outward. This is the one that allows relativistic flight. This does not allow relativistic flight for reasons having to do with just fundamental physics of conversion and what it means to have a ultra high speed ion engine. You're basically ending up with a flashlight in that ultra relativistic limit. So basically, once you project power, you can do a lot of things with that power. And these are a couple of cases. We've got more than 60 papers and a long book on the subject if you're interested. This is part of our map to the future, where we start in the laboratory, in which we are now, going to outdoor testing, and then looking at, say, Earth to LEO, MEO, GEO, and then lunar as a path forward in the not too distant future. But there's a long-term goal here, including fast solar system missions, as I mentioned, and then going outside of our solar system. Lots of science to be done, lots of technological developments that I'll speak about, not too much detail. And it's really a scaling issue. How do you scale from small to large? And that's part of the technological path that I'll discuss. Okay, so what we have is a program that starts kind of at its core, is a directed energy phased array, which allows for scalability. And then in the case of the LSI program, we built a beacon which can go on the moon that we can phase to. We're working on diffractive optics, which allows us to have much lower costs and low mass, particularly for space missions. We've done a lot. We have a huge amount of work going on in fiber optics and photonics, and then in algorithms to make the whole thing work as a unit. Okay. So I'll give you a quick overview of physical optics. We are working with roughly 750 millimeter diffractive optical elements. They kind of look like Fresnel lenses, but they're quite a bit more sophisticated. They can be stamped, so hence you can go to very, very low cost items. I'll show you our ground lens equivalent approach to that, which is an f7.5 at prime focus. Those work really well. They're very, very close to diffraction limited. We've already integrated multiple elements of that. That works well. Done a lot of work and built fiber tip actuation. Our system is currently fiber based, but longer term you want fully semiconductor based. This works well in terms of taking out the first order tip tilt corrections in our atmosphere. Again, you want to be in space, but you start on the Earth for economic reasons. Currently, we're cranking out a couple of sub-elements per week. These are full-blown systems. I'll show you in a moment. And if we had the money, we go to an external fab house and say, here, make us 1,000 of these or 1,000,000 of these or whatever. It's an economics issue. We've developed a fully digital, extremely sensitive near photon limited frequency FPGA-based system that works. I'll show you a little more of that. So here's some hardware. This is the FPGA-based system for phase locking, and then I'll show you the photonics. It's a lot of electronics, a lot of photonics. I don't want to bore you with all that, but that's unfortunately what you need to do at this point. Here's some hardware. Here, this is not CGI. Okay, this part's CGI, but this is real. So we're building up hardware. We crank out of order 1 to 2 of these per week. These are full-blown sub-elements, and you array them in whatever size array you want. So they have all the electronics, all the photonics. You just put in power and a fiber, and they're completely self-contained, including all the thermal management. You can see the first order tip tilt section here, and the final optics here, which are set at 10 centimeters. The reason for the 10 centimeters has to do with the atmospheric perturbation, so-called free length in our atmosphere for reasonable sites. In space, this doesn't have to be 10 centimeters to make it anything you want. Our algorithm for phasing is a nested loop, nested tree algorithm, which allows us to phase numerically. We've done simulations. We've done over 10 billion elements numerically converge very rapidly. And we don't have the money to build 10 billion elements, but if you did, you'd have yourself a relativistic capable systems. Anyway, the reason for the complexity here is the Earth's atmosphere. Again, you'd rather be on the moon. So this is a CGI, but then I'll show you the real thing. This is real down here. These are sub-elements. Each sub-element, again, has an optic, which is about 10 centimeters in diameter, and you make arrays out of them. Every element is identical to the other, so you can, in theory, mass produce them. And we're, quote, mass producing them in our lab at the rate of a couple per week, about 2 per week. Okay, everything is on board. All the photonics, all the electronics, all the thermal management. It's really pretty sophisticated. These are fully bidirectional systems, which is something unique that we developed. So we have a greater than 10 to the 12th, greater than trillion to 1 dynamic range. So we can simultaneously broadcast high power and receive ultra low power down below a nanowatt. We can actually operate with about 100 picowatt beacon per sub-element. Anyway, these are just some curves of output power versus pump power, pump current. Anyway, this is real, not CGI. Okay, thermal management back here is a bunch of fiber photonics. On the backside is electronics. And then this is the fiber tip actuator, which does the first order tip tilt. You can scale this up. We're currently operating about 10 watts per sub element. You could go to 100 with this. This is a single mode system. If you go to kilowatt range, you radically change the some of the photonic issues. So we would probably stick at roughly 100 watt per sub element, which is sufficient for our purposes. This is what it looks like in drawing. These are the prime focus 10 centimeter diameter lenses. And then each of these, again, is one of those sub-elements. So currently these are carbon fiber tubes, nothing magical about that, just relatively inexpensive and very stiff. Okay, so sub-element optics. So one path forward to reducing the cost, for example, here, these are ground lenses. Ground lenses are expensive. Nothing that couldn't be done, and we do it, but it's not the way to go when you want to build 1 billion of these things. So we're working on stamped diffractive optical elements, and we currently have our f7.5 750 millimeter focal length refractive system working. So these are ground lenses. It works really well, very close to diffraction limited. We also have some f2 systems that work well, but we prefer the f7.5. And we have our first diffractive optical elements that are stamped from a master, but we are refining that to get better performance. We're not quite diffraction limited on those yet, but we have a path forward. Anyway, diffraction optical elements are fairly simple to conceive. It's kind of like a lighthouse lens, but not really, because these are designed to be diffractive elements rather than just refractive elements. But basically, you make a master, and then you stamp it like a DVD or a CD, and then you pull off the stamped elements. But in theory, we could make the lenses for pennies, literally. If you look at how CDs are made, you can make those for pennies. So this is a path forward for cost reductions. Okay, just some figures of measured Strels, beam patterns, basically, in the focal plane. This is 1064 nanometer light, so this is part of our ytterbium laser system, and just showing that we achieved pretty close to diffraction limited performance. These are smaller lenses designed for a high atmospheric perturbation testing case. Okay, so both the 1 inch and 4 inch, sorry about the mixed units here. The smaller ones at 25 millimeter and the full scale 100 millimeter optics are very close to diffraction limits. So this part works, at least in the refractive case. We're working on the diffractive case currently, as I mentioned. So this is a case for doing high turbulence measurements. So when you want to test this on the ground, one of the things you want to do is start with a horizontal test range. The problem with the horizontal test range on the ground, as we've seen from some DoD testing we've done, is that you run into a lot of perturbations, not unexpected. But to overcome that, we have a simple way of modifying our system to be able to deal with very high, what are called CN squared fluctuations, and do both ground level testing in pretty bad environments as well as in nicer environments. We run a high altitude test range, for example, at 4 kilometer altitude, which you don't have to do this high turbulence environment, but this allows us a lot of flexibility in testing. So here's this is not CGI. Okay. So here's the full scale 100 millimeter lenses. You can see the anti-reflection coating pretty clearly. And then here's some of the 25 millimeter ones that are designed for higher atmospheric perturbations on a mount, and it works. It's a pretty cool little test system. So here's where we do beam testing. We can overlap beams on a target, kind of sort of hundreds of meters away for testing, and so far that part is working just fine. Okay, photonics and active systems. So this is where this is the really hard part of the system. The optical stuff is a pain, but we know how to do it. The photonics we know how to do, but it gets really complicated, and the path forward the real path forward to building billions of these things for these enormous missions requires an approach which is a really photonic integrated circuit class approach. Anyway, this is real data based on a system in our lab, and you can see each in this case 7 elements in the system. These are the beam patterns of each of the systems, and then we beam combine, make a phased array, and then you end up with this. And the reason there are side lobes here is because we only have 7 elements in this case, so you get a lot of grading lobes, and then you can move things around. And I'll show you a movie, and you can watch a movie. This is with atmospheric perturbations with the beacon off. We'll lock the beacon in a moment, and you'll see that so now we're beacon locked. Okay, so beacons from the target to the phased array, and once you lock onto it, locks in less than a millisecond. It's very stable. Then we turn the beacon off, and the atmosphere does its thing. Okay, progress. All right, so we've pretty close to photon limited at 100 kilohertz loop closure rate. And this is dominated by 2 things. For ground-based operations, again, you have the atmosphere. Also, for large baselines, you have fiber phase noise. So if you're interested, you can read our many dozens of papers on this, and talks about all the nitty-gritty of what's going on here. So even in space, if you had a fiber interconnect, you'd still have to deal with fiber noise. But we've shown that you can close the loop fast enough to deal with that. We've gone out to 25-kilometer baselines, 25-kilometer radius baselines, 50-kilometer diameter, which is enormous. You don't need that for sending small robotic probes to the nearby star systems, but we've shown that we could do it anyway in the lab. And very close to photon limited. Again, the longer-term approach is really you're going to need a large NRE to do this, but you want a fully integrated photonic integrated circuit based approach. We have a very large photonics group at Santa Barbara, and so we're working on paths forward with them, but this will require significant development. Right now, what we have works. It's just not optimal for building huge arrays, but it is optimal for doing things right now from ground to space, for example. So we have things we can do already. Space-based deployment, going on the moon, for example, is something that should be looked at for these programs in the longer run, using the moon, for example, as it's kind of a stepping off point for going to Mars. Okay, DE systems, we now have full 7 elements systems that we'll be making many more of to increase the size out to at least a meter. A meter will get you out to low Earth orbit, by the way, for starting testing in ground to space. We can increase the production rate by using external fab sources, but we can do it all ourselves. Just it's not the optimal thing. It's like making circuit boards. You'd rather have somebody else do it for you. The diffractive optical elements are working. The Strel is not as high as we want, so we're looking at various ways of making better masters. We're looking at diamond turning options at the moment, so we'll keep you posted on that. We do have full-size DOEs, but again, the Strel is not as high as we want. We've done a lot of work on algorithm development and phase shifters, which are lithium niobate. So there's a lot of stuff going on there, but it's probably more in the weeds. And then this really has to be taken into account. If you want to do this, the right way to do it is go to space. Okay, so we're actually exploring a lunar test and flight system. And that is it. So I guess I'm early by 2 minutes and 15 seconds. So I will stop.
Wow, Phil, you're early. Oh my goodness. Well,
Yeah.
you're getting smooth with this, man. This is awesome.
No problem.
Good job, man. Good job. No, it's always great to see your talks. Very rich with a lot of real things and making good progress. So great stuff. I think I saw a question or 2 come in on YouTube as well. I'm trying to monitor multiple things here, and Shock is helping me with that. We're going to take the questions. We get to a kind of like a facilitated Q&A at the end of all the talks around just after 2 o'clock. Probably around 2:20 is where we might finish. It might be a little long because the talks usually there's so much good stuff. I don't want to stop people, right? So, okay. With that, up next, we have Adam Kay and John Bush from MIT. We're going to be talking about going back to the frontiers of physics again. They'll be talking to us about their project titled Dynamic Vacuum Models of the Electron. And so with that, I'll hand that over to Adam and John, and I will give you guys a two-minute little ping when the time comes. So
Great. Thanks, Sonny. I'm going to share my screen real quick. How's that look?
we got it.
Great. So let me do something real quick. All right. Okay, so thank you very much. I'm going to give a report on our progress. Just a refresher for the orientation. This is hydrodynamic quantum analogs. It's a research project or program that was instigated in 2005 by Yves Couder and Emmanuel Faure. There is a millimetric drop of oil that is bouncing on a bath of oil, and there turns out to be a particle wave association. And now there are dozens of quantum analogs between this system and various results in quantum mechanics, which is very interesting because we've been told for about 100 years that quantum mechanics and classical mechanics are fundamentally different. So we have been looking into the 3D case for the particle. The two-dimensional case is pretty well understood at this point, and here is like a kind of summary of the results that were obtained over many years of research. And it shows like the regime diagram of what happens with various parameters when you change the system. You get responses to perturbations that are overdamped and underdamped. And the top of this regime diagram, you have erratic behaviors. In the left, you have like a orbital spin state, and so on. So this is a generalized model of the droplet bouncing on a bath of oil. And this has been limited. The entire research program has been limited so far by 2 dimensions. So we extended this with the help of LSI into a 3D model, and we make the wave kernel a spherical Bessel function. In the 2D case, it's a cylindrical Bessel function, so that's a natural extension. And we took the model that they developed. John Bush, Matt Dury, many other people developed the 2D model, and we extended it to 3 dimensions this way. So we have a trajectory equation, and there's really very little difference between this and the 2D equation. The main differences are the leading factor of 3, which is because we're in 3 dimensions now. And then the wave kernel here is cal H, which is, as I said, the spherical Bessel function. This system depends on 2 parameters alone, the kappa naught and gamma, and they express essentially the inertial resistance of the particle. It's like dimensionless mass. And then gamma is, you can think of as memory. It's bounded between 0 and 1. And at 1, you have infinite memory, which is like the force of the wave field. So the wave field persists over an extended period of time, and we can tune that persistence with gamma. So here's a kind of gallery of some of our results. So in the 3D case, we very quickly got the walking state that we also observed in the 2D case. And in the top left here, you see the wave field for a stationary particle before it has started moving. And that would be equivalent to equivalent roughly to like 0 memory. And then for B and C, you see the wave field for 2 different walking speeds, and they're strictly a function of gamma, the memory. And here we have the middle one, B, which is slightly slower, and as the speed increases, the wave field becomes more persistent, and it has this kind of horseshoe shape. So another thing that we observed is chaotic behavior. With very high memory, you get this kind of like space-filling, random diffusive walk, which was also observed in 2 dimensions. In that case, it was related to the stochastic mechanics of Nelson, who has a diffusivity constant, which is very, very close to the results here, and they're actually rationalized in this case from the fluid dynamics properties. So they depend on the wave field, the wavelength, the Faraday wavelength most strongly. We also uncovered some novel results, which is a helical spin state. This happens in higher memory, and we spent a long time investigating this. This does not occur in 2 dimensions, obviously. We have a kind of like a corkscrew pattern that travels through space. And this is what it looks like. I wonder if I can get them both going. There we go. So on the left-hand side, we're kind of like cutting the XZ plane, and like Y is 0. So you see this thing traveling upwards. And then on the right-hand side, we're traveling with the particle as it goes upwards into the Z dimension, and we can see how the wave field changes. So there's some interesting things here. We found actually a double quantization in this system. So the radius is quantized by integer multiples of the Faraday wavelength, which is very similar to the 2D spin case. But we also have an extra degree of freedom, which is the pitch angle, and that is also quantized. So in this plot, what we're showing is the solid, these solid lines are the existence lines for the various solutions that you can get for these spin states. And everything above these lines, there are parameters, the selections of parameters that actually solve the equations. And so we have the black one is this one here on the bottom. The blue one is one integer multiple of the wavelength larger, and so on for the red and the green. But then the dashed lines is the same thing, only we have a higher pitch angle. So the helical state has this double quantization, which we thought was very interesting. Quantization is we're very used to seeing quantization in the hydrodynamic model. It emerges in multiple different settings, and it's largely rationalized through the monochromatic features of the Faraday field. So here's like the summary tying it all together in 3 dimensions, which is the analogy of the 2D plot that I showed originally. So this is the regime diagram for the free particle in 3D. And we have the walking state. We have overdamped and underdamped regimes for the walking state. Up here at the top, in this kind of like scallop shape, is the chaotic regime where the particle can do this kind of random walk. Here on the left is the red region of stability for helical spin. So these are stable states. You perturb them and they remain going in their helix. And then here we have an overlap between the two, where we have both chaotic states and helical spin. So this paper is now done. We are submitting it eminently to Proc Roy Soc, and it's been very, very helpful to have LSI support through that. So the other thing that I wanted to say is that by thinking about the helical spin, and in particular in trying to relate it to the electron, and thinking, hey, maybe this helical spin has something to do with electron spin, we came to some pretty interesting places, but they were not what we were anticipating. And I think that anyone who does basic research has had this experience where it's not like the thing on the left where you're going in one direction and you just keep going. It's more like the state on the right, where you are sometimes don't know where you're going to go next and wind up in surprising places. And that's what happened in this case. So I have some new results to report, but they're very different than what I was expecting to report. So here we go. It has to do with Bell's theorem. Now, people who know about the foundations of quantum mechanics will know about this. It is very much at the heart, I would say, of fundamental physics at the moment. And you'll probably be aware that in 2 years ago, 2022 now, I guess, the Nobel Prize was awarded to the experimentalists who first set out to test whether Bell's theorem, Bell's inequality, was going to give the results that quantum mechanics predicted. And it did. So 60 years or so of experiments have shown that, well, I guess a little bit less, 40 years of experiments have shown that quantum mechanics is confirmed. And the assumption is, well, the result of Bell's theorem is to say that, well, reality cannot be the way Einstein imagined it. So that's local realism. That is, you know, the atom, the particles have an actual state. They actually have an actual position, even if we can't talk about it right now. And the way, whatever the atom or the particle is doing is determined by the laws of motion, whatever those are. And this is what Bell's theorem supposedly disproves. And it was meant to be, it's taken to be the final blow in the Bohr-Einstein debate, where Bohr finally won. And let me just try to explain this briefly to situate the results. So the way that these tests are set up roughly is you have 3 different measurement stations, say they're manned by Alice, Bob, and Carol. And each person has a measurement angle. So they have a polarizer, they have a magnet, and it has some specific angle that they set it at. So Alice's might be at 0, Bob's might be at, say, 90 degrees. And then what you look at is theta AB, which is the difference between Alice and Bob's angles. So if there is no difference, if they're at the same, well, the next thing you do is you have a source of entangled particles that are between Alice and Bob, and it shoots entangled particles to both of them. So one particle goes to Alice, one goes to Bob. These particles are entangled, so they're described by the same wave function. And what quantum mechanics predicts is essentially a correlation between what Alice and Bob sees, what they see based on their magnet angles. If Alice and Bob have the same magnet angle, then the correlation for the singlet spin state, where you have one particle with a spin up, another particle with spin down, correlation will be -1. Now, as Bob changes his angle to differ more and more from Alice's, the correlation changes like a cosine. So when it's orthogonal to Alice, there will be 0 correlation. And then when it is opposite to Alice, then whenever Alice sees spin up, Bob will also see spin up. So what we do is we take this specific setup between 2 people, and we do it 3 times. We do it between Alice and Bob, and then we do the same thing between Alice and Carol has a different angle than Bob. And then we do it between Carol and Bob. So that's the basic setup of a Bell test, even though this is not how they actually do it in the lab. This is kind of like this is the thought experiment of what you would do. So here's Bell's inequality. This states that the correlations that you see in the 3 different arms of this triangle have to satisfy certain bounds. And quantum mechanics predicts that the correlation in all 3 cases will essentially be negative cosine of the angle difference. So theta AB, theta AC, and theta BC, you just plug in the cosine, and then you find that this inequality is false. So that's the problem. It's like, well, you derived this inequality, and it should be true, but quantum mechanics predicts that it's false, and experiments have shown that it's false. So the assumptions behind the inequality have to be wrong. And those assumptions are local realism. So these are the stakes. They're pretty high stakes. Now, the thing to note, though, is that each station has to produce 2 sequences. And so, you know, when Alice is here measuring her correlations with Bob, she's generating a sequence with Bob. And now she has to go and do it with Carol, and that's a different sequence. So Alice has generated 2 sequences now. And the same thing with Carol and Bob. You know, each one generates a sequence with Alice, but then each one generates another sequence with each other. So all 3 have generated 2 sequences. And so now there's like kind of an ambiguity. So we have A1 and B1. This is the first thing we're doing. A2 and C1, that's the second thing we're doing. And then C2, B2, that's the third thing we're doing. And this is the closing arm of the inequality. And we always do basically a fresh experiment each time to get the correlation, and that's quantum mechanics predicts that the correlation will be the negative cosine of the angle difference. But the thing is, what happens if we look at C1 and B1, the correlation between C1 and B1? In current experimental methods basically force the correlation to be 0 because we can't reproduce the same stream of particles and send that same stream to Alice each time. So the correlation between A1 and A2 is always going to be 0. It's like flipping a coin on 2 different days. You flip a coin 100 times on 2 different days, the correlation between those 2 sequences is going to be 0. But if there was some way of us enforcing A1 and A2 to be the same, we could even do it in a thought experiment, then, you know, the correlation between B1 and C1 is no longer necessarily 0. And in general, the correlation between B1 and C1 and the correlation between B2 and C2 can be totally different. So just think about this random thought experiment where, you know, Alice and Bob first just do all black balls. Maybe they're drawing them from an urn. And then Alice turns to Carol and they have a different urn. And Alice and Carol draw all white balls. And so the correlation between B1 and C1 is going to be -1. They're always opposite. But maybe Carol and Bob have a third urn and they turn to that and they draw, but those urns, you know, there's equal number of black and white balls. And so their correlation, C2 and B2, is 0. And the point of this is that it makes a difference. Like the correlation between B1 and C1 is not necessarily equal to that between B2 and C2. So if you enforce the correlation between B1, if you enforce the A1 and A2 are equal, you can compute the correlation between B1 and C1 versus the standard correlation between B2 and C2, and you get very different correlation functions. They are both predictions of quantum mechanics. The one on the right is the one that everybody uses to violate Bell's inequalities. The one on the left is what you could call an implied correlation. We can't test this right now with experimental tests because the only way to do it is to shoot an identical stream of particles to Alice both times. And we have no way of doing that right now. So what's going on here? Actually, to understand it, we need to take a little bit of a detour back about 100 years. So as it turns out, the English mathematician George Boole considered actually the identical problem to Bell in 1862. And he wrote about it, and what he was considering were joint probabilities between 3 events, A, B, and C, and what are the logical conditions that need to hold between these joint probabilities in order for them to be consistent. Because you can come up with 3 joint probabilities between 3 events, A, B, and C. So you look at the probability of AB, the probability of BC, probability of AC. You can come up with numbers that are logically inconsistent. And they're constrained because they're in a triangle. You can pick any 2 of them to be almost anything you want. But once you do that, you are no longer free to pick the third one because they're in a triangle. So this is actually the result that Boole found 100 years before Bell. It's the same, except there's a difference in sign. So Boole's inequality has this negative sign here. And that's kind of interesting. So, you know, you take a look at that, and what happens when we plug in this implied correlation between B1 and C1 into Boole's inequality? Well, actually, it satisfies Boole's inequality. It violates Bell's inequality. So this implied correlation doesn't help us escape Bell's uncomfortable result. And certainly the standard quantum mechanics correlation of negative cosine violates both of them. Okay, so this implied one is interesting. There's this one, seems like one little crevice of light that is like maybe going to let us escape from this result. Now, what is the origin of the sign difference? This is the thing that we need to understand. And if we go back to Bell's derivation of his original inequality, we can find out. And this is I basically just screenshotted the relevant equations here. Okay, so we don't really necessarily need to even understand them. We can treat them as definitions. This first line, let's just treat it as a true definition. We'll assume it's true. The second one is also a definition. And then the third line is the result of applying the second definition to the first definition. All we've done is we've switched this B into an A. And because we can do this, we have to switch the sign. It becomes negative. So now Bell has a derivation. It's very simple. It's only a few lines. And the penultimate step results in this inequality right here, where we have these, this is the absolute value that you have on the left-hand side, and we're about to get the right-hand side of Bell's inequality by just doing some basic things. And this is actually where the origin of the difference in the sign between Bell's inequality and Boole's inequality comes from, because it's an error. It's an actual sign error. So if you look at it, you have a big A here, and we're going to need to use this identity to flip the sign to make this B. But then we have another A here, and we need to use this identity again to flip this sign to make it C. And so we flipped the sign twice and it stayed negative. And what Bell did is he looked at this and he failed to realize that you say, oh yeah, you have two big A's and that's what you have here. So we only need to flip the sign once. But what he failed to realize is that you have one of these, and here is an A. And we have 0 small A's in here. So there's actually a sign error, which is just kind of crazy to imagine and very surprising. So Boole's inequality is actually the correct one. And I went and Googled this. I was like, hey, has anyone seen that there's a sign error in Bell's inequality? And the answer is no. But I did find a lot of commentary on sign errors. And one of them was this. Long ago, as I recall, a physics prof stated something like, according to Eugene Wigner, half of all math mistakes are screwing up minus signs. I think this is probably true. For a little entertainment in discrete math for CS major classes, I convey that story the first time I make a sign error. Then I put a chalk mark on the wall above the board to keep a running total and estimate the likelihood of finishing the semester in single digits. So I do have a few more things to report, but I will end there. I want to just thank Sunny and LSI for allowing the freedom of basic research. I think that you can't really make fundamental advances in knowledge that are not accidental without allowing for basic research and a good deal of leisure and freedom. And because of that, I think the institutes with bold mandates like LSI will have a very big impact. And one example of this is the fact that I actually have a book coming out in 2 months. And this book was made possible by my work at MIT with John. And that work was made possible by LSI. So without LSI, we wouldn't have any of these results. I wouldn't have had the chance to work with John at MIT, and this book would not exist. So I just want to thank Sunny and LSI again. I think what you guys are doing is very, very important, and I really appreciate the opportunity.
Thank you, Adam. Absolutely wonderful. Always love to hear your talks. I always feel like I'm just learning so much. It feels like somebody who knows more about the secrets of the universe is kind of peeling back the veil a little bit and letting some of these things out. So it's always kind of a thrill. So that's great stuff. And I gotta say that's a pretty titanic find that you highlighted there at the very end. Looking forward to chatting with you and John about that offline. Definitely want to follow through on that. Need to get that in the peer-reviewed literature ASAP.
Yeah, as soon as possible. Yeah.
Right. You might not be able to get it in Nature, but I'm sure you can find another good journal that's willing to, hey, math is math, so it doesn't matter, right? So awesome. So again, we'll be saving questions until we get to the facilitated Q&A here a little bit after 2 o'clock. So let's go ahead and press ahead. We have 2 more talks. We have an amazing talk coming up here with Jerry Carson at the University of Maryland. I believe Ray Sedgwick is unfortunately right now at this exact moment right in class, so he couldn't make it. But Jerry is carrying the water So Jerry, you have the con, and I will give you kind of that 2-minute squeak when the time comes, just to let you know. So you go ahead.
Okay. All right. Can you see my screen?
Oh, sorry to interrupt. Ray did make it. Yay! All right, Ray.
Yeah.
You made it.
Yep. Can you see my screen?
Yes, sir.
All right. Just a second. Let me get where I can see it. All right. So again, just like to repeat the thanks to Sunny and LSI for sponsoring this research. I think we've seen a lot of interesting things today, and hopefully we can walk through a couple of results which you might find interesting. I'll be presenting today for myself and for Ray, who is the PI on this task. We're going to be looking at direct fusion drive based on centrifugal mirror confinement, and we'll start off with just a review of some stuff we talked about the last time, how centrifugal mirror confinement works, and how we integrate that with a propulsion system, and dive in at that point to some new developments in reactor dynamics and propulsion performance, and then talk a little bit about our conceptual engine that we're using for our balance of plant and mass properties estimate. So centrifugal mirror confinement is mirrors combine magnetic and mirror confinement with a high E cross B drift velocity. The resulting radial and axial forces confine the plasma to a well. It's an annular plasma region where thermonuclear fusion conditions can be attained. And if you look at the schematic in the lower left, you see the mirror magnets and that impose those green B field lines, and then the outer and inner central electrodes, which generate the E field, and they result in a plasma well, which is, for this configuration, a donut-shaped region that where the fusion happens. The schematic on the left is simulated. The simulation of that schematic is shown on the right. It's bisected at the midplane, so that white region to the left is 1/2 of the plasma. CM's been demonstrated in the U.S. and Sweden and in the Soviet Union in the 1950s, 60s, 70s, and 80s. More recently, the Maryland centrifugal experiment in the 2000s demonstrated a confinement of a 100 EV plasma. So that was progress on their way to where they are now with centrifugal mirror fusion experiment. It's a follow-on to MCX, and you'll see a photo up there on the right of the current state of the experiment. It's a collaboration between UMD and University of Maryland, Baltimore County, being funded by ARPA-E. They are currently doing limited experiments with deuterium and hydrogen, and but mostly we're just working on getting their instruments refined to the point that they can get their burning plasma experiments done start of the second half this year. For a propulsion application, the centrifugal mirror would be operated in tandem with a warm plasma propulsion system. Here's just a simple schematic of the system. We have the reactor in the middle, and particles are leaving through both sides through the mirrors, and on the jet side, the right side, they enter the propellant, heat the propellant, which then passes out to generate thrust. On the forward side, particles leave and enter a direct energy conversion system. In our case, it's a standing wave direct energy conversion system, and that produces the power to run the reactor. So that kind of brings us up to where we are. During the first half of the grant, we concentrated on deuterium tritium systems, as that gave us a lot of insight into the reactor and the warm plasma. Since the last time we talked, we've updated our reactor model to include more reactions, and now we're focusing on deuterium and helium-3. But before I talk about some of those results, the results you see here on this page are from the DT tests. We identified something we call the critical Mach number. And the plot to the left is the Mach number as a function of the mirror ratio being the ratio of the mirror strengths and the mid-plane magnetic field. And for our systems, we like to keep those relatively low to allow as much material as possible to go to the propulsion system. But in these systems, intuitively, you would think that the higher the Mach number, the lower you would have to have the mirror ratio. Well, that's true up to a point, and that point is the critical Mach number. Above that point, the thermal ions are relatively well confined, but the fast fusion products are only mirror confined. They're not centrifugally confined. They continue leaving at the same rate, but it's a lot more expensive to replace them at the high Mach number, so the system responds by increasing the mirror ratio again. And that's the behavior we see repeatedly, no matter what fuel we're running and what conditions or regime we're running. It's also evident from these data from the simulations that viable solutions for self-powering reactors tend to operate in the vicinity of the critical Mach number. And you see on the second curve, the QA equal to 1, that is a break-even point where the reactor is self-powering. And the Mach number for that is relatively close to the critical Mach number, just a little bit higher. So it's clear we'd like to know what this, it would be convenient to know what this critical Mach number is, so we don't have to do lots of simulations and sift through data. You can observe the critical Mach number from the data, but looking at the thermodynamics, the hypothesis is the critical Mach number is the point where the energy losses from the thermal species equal that of the prompt fusion species, and that's what that relation in the bottom right is. The higher the energy of the thermonuclear reaction, the higher the Mach number. Now, I should say that sigma energy is for any primary reaction as well as any relevant side reaction. So for a DHE3 system, that would include both the deuterium and the deuterium-tritium side reactions. In the denominator, you have the plasma temperature, and that 1.82, it's not a curve-fitting value. It's actually thermodynamically derived. It's technically, or theoretically, it is the ratio between the rate of thermal ions leaving the systems to the rate of prompt ions leaving the system. And that number is pretty stable in the vicinity of the critical Mach number, about 1.8 to 1.84. So given that relation, you can stake out a lot more quickly than we used to be able to do, where to look for a viable solution. On the propulsion performance side, we did go back and look at the data from all of our simulations on our 1D warm plasma model, and we're able to infer some other parametric relations describing the behavior of the warm plasma. Fusion energy deposition depends on transport properties, and as you can see on the chart to the left, the electron collision time on that blue line is a lot lower than the corollary for the propellant species. So the electrons heat up a lot faster, and for light nuclei, they pass on that energy relatively quickly to the ions. So you see the temperatures tend to equilibrate, as shown in that middle curve. For heavier ions, if you say you have a nitrogen propellant, the heat transfer to the ions is much less efficient, so you end up having a very high temperature electron gas and relatively cold ions. And that's a fundamentally different type of plasma. So when we wrap all this together and try to get a propulsion efficiency out of it, that curve to the right started out as a plot of simulation cases, and the question came up, why are they grouped so closely together? Well, did some analysis and found out there's a relation that follows a specific impulse. The higher the specific impulse, the higher the efficiency tends to be, but with the caveat that there's that chi factor that if you have a lot of ionization energy, then that tends to lower the efficiency. So that is the case with heavier nuclei, where you have a high temperature for the electrons that results in multiple charge states, high Z's, so that it draws the efficiency back down again a bit. So, you know, these relations, including the maximum theoretical efficiency just below the first equation, are again helpful in characterizing the systems as we do our planning our simulations. Is very helpful in doing that. So that brings us to an important part of our task with LSI is to characterize with some degree of rationality what the mass properties, you know, for a system might be. And this is our design cycle 1. There's a 1 megawatt jet power delivered using D-helium-3 as a fuel. It's a 96 keV plasma. Expect to operate it off of ammonia or water as propellants. Those are good because they have a very high storage density, but they also have a very high hydrogen content once they're dissociated and ionized, and that makes for an effective propellant. This particular model has an 80 kilowatt neutron power from the side reactions, and is fairly effectively mitigated by the flight weight shielding in terms of protecting the magnets. So you see the major components there: the reactor in the middle, the standing wave direct energy conversion to the left, and again, these are all the proportions are all correct for this particular design. And the propulsion system, the reason why it's a little bit wider is we only have the mirror magnet and the nozzle magnet. We don't have field magnets to constrain the plasma, so we have to let the plasma expand to the last good flux surface. You'll see also reservations for the power electronics, which take the power from the SW deck and turn it into power usable by the reactor. So moving on, I haven't completed the mass properties analysis, but the 25 kilograms per kilowatt looks feasible at this point. The reactor and the SW deck were scaled based on a best in class current of DHE3 solutions. That's 800 kW per meters cubed. And although at this point the propulsion performance calculations are parametric using the relations from a couple of charts ago. A couple of technology assumptions that we'll get flight weight radiation tolerant HTS magnets. We're not going to be able to do a 20,000 ton or 20,000 pound magnet like Spark has for 20 Tesla. We'll need to have 20 to 30% that weight. The power electronics also have to be similarly scaled. Fundamentally new architectures are probably required, not necessarily new technology, but new architectures. Anticipate using liquid metal heat pipes for the thermal management system. And also because the system is very effective at confining the plasma, we're going to have a buildup of helium in the reactor well, which we'll need to mitigate somehow. And so we need to get a better insight into the transport of those species in the reactor, so we'll understand how we might be able to remove them. The characteristics in these tables on the right, the key numbers on the reactor is the Mach 13 Mach 11 operating for the reactor, and a 1.5 megawatt output power from the reactor. And by the time you get a 70% or so propulsion efficiency, that gives you a 1 megawatt delivered. So some observations. As I said, we spent a good part of the first part of the grant looking at DT solutions. But when you start looking at actual systems and the sizes of things and the structures, you quickly come to the conclusion that that these are problematic because the neutron fluxes are so high, and the shielding is prohibitively heavy. It's true that there are plenty of neutrons to self-power the reactor, but the thermal conversion cycles are heavy, and the efficiencies are 35 to 45%, which means you're going to have to dissipate the balance to space, which means very large radiators, which we prefer to avoid. By contrast, the DHE3 systems provide high power density and low neutron flux. The downside is that the E fields scale with the square root of the electron temperature. So the biasing potentials for these systems are 2 to 3 times higher than that of a DT. Back again to the idea of the critical Mach number, it's across the board. We observe that the jet power is maximized when the reactor operates in the vicinity of the critical Mach number that's shown in the curves to the left. Finally, just a reminder that there are development required for the HTS and power electronics that are needed to make a overall viable propulsion system. So those would be separate and apart and challenges in their own right. I just want to remind folks that this is a system what we're looking at, and there are some developments necessary to make the system as a whole work. So next steps, the propulsion calculations this time around were parametric. I need to update the warm plasma 1D simulation to account for the deposition and characterize the deposition of these different types of high energy species from the reactor. Do some more analysis to see if there are any higher performing DHE3 design points that we can use. At that point, I'll go back and complete the balance of plant design with a cycle 2 and try to get to a 5 megawatt jet powered position type of system. And then the final part of the task is to develop conceptual design for experiments to characterize the reactor and warm plasma interface. We've made a fair number of assumptions about what the interface looks like. And we have some analytic approaches we can do to do that, but we're also going to try to do some experiments possibly based off of CMFX reuse to evaluate that experimentally. And I think that is all I have for today.
Thank you, Jerry. Appreciate it. I was taking some notes there as you were going through that. Got some questions for you later when we get to that point. I just will simply say it's nice to see the evolution of the maturity of the concept, right? Thinking back to some of the original pictures and schematics and thoughts, like even in the proposal, right, versus some of the slides that you showed today. It's kind of neat to see, all this work, all these layers that you keep adding, right, every time you continue to look at the details. It's good to see that. So,
well, thanks. I would like to mention that SPPL is a team, and I am borrowing from my teammates' work at UMD and Dr. Sedgwick's team. So again, we just like to repeat thanks for supporting this research, and look forward to closing this out and getting you some leave behinds that will justify your supporting us.
Yeah, thank you, Jerry. Appreciate it. All right, pressing ahead, we've got our last talk for the day, and then we can get into some questions. Joining us from the opposite side of the globe, both in terms of east-west and hemisphere, we got our good buddy Chathura Bandutunga joining us from Australian National University over in Australia. And the title of his project is Navigating the Atmosphere, Transferring Terrestrial Beam Energy to Light Sail Spacecraft. So Chathura, you have the con, and I'll give you like a little audible, hey, you got 2 minutes type of thing when the time comes. So
sounds great. Thanks, Sonny. I'll just share my screen. Just confirming that's all good.
We can see it, yes.
Can people hear me clearly?
Got your 5x5.
Excellent. Well, thank you all for joining and listening in today. It's early here, but it's great to be with you all. I'm Chathura. I'm from the Australian National University in Canberra, Australia. And we've had a team looking at optical phased arrays for a number of years now. And one of the interesting things that we were considering is how we can make optical phased arrays with the size, scale, and kind of control that you need to transfer ground-based optical energy to propel light sail type spacecraft. And with the generous support from LSI, we've been able to take some of our concept ideas, which we developed, and really flesh them out into hardware. And now we're going from the digital signal processing system, which has been developed in this project, and launching into an optical test. Before I begin, I'd like to just acknowledge the ANU team, which consists of Noah Baldwin, Paul Sibley, and Mike Ireland as well. And the group of us have been working quite closely on this project for the last few years. Let's see, next slide. Just to provide a general recap, a general overview, the premise that we're trying to, that we're working with is that we'd like to use light and the energy that it carries to power space travel, and power space travel that's able to access speeds that are not really attainable using conventional chemical propulsion. To do this, this is not a new idea, but what it requires is the ability to deliver a large amount of laser power to a sailcraft. And for this, you need a large synthetic aperture array. So an array that comprises of a large size, but can be made up of many individual apertures working in concert. And the reason for this is that the large size allows us to get a small spot, laser spot on the sail, but it also allows us to scale the power on the ground to reach the megawatts or gigawatts of laser power that's usually required. Now, shooting light in through the atmosphere is great and all, but we need a way of integrating some atmospheric measurement and correction for this array. And this is a fairly significant challenge due to this array's size and the number of elements that make up this array. And so ANU and the team that I just mentioned, we developed an architecture that allows us to modularize the approach to both controlling the array from internal measurements, so stabilizing the array itself, but then also to take that a step further and measure and correct the atmospheric turbulence across the entire array using a beacon spacecraft. And that's kind of flow chart down in the bottom right describes that process. And in this project with LSI, what we've been able to do is really nut out the nuts and bolts of this atmospheric correction signal processing chain. So if we just zoom in on that image and start from the beacon spacecraft itself, we can walk through what's going on here. So we've got a flat wavefront coming in from the beacon spacecraft. This is within the isoplanetic angle of the laser sail at launch. This wavefront sees the atmosphere that the array is now passing through in the opposite direction. And so it picks up the relevant phase shifts across that beacon field, across that beacon wavefront. What we've designed is a method to internally sense and measure those individual phase front components as seen by separate apertures within this array. And having those individual measurements allows us to do a nearest neighbor type approach to distributed control of each of these apertures, which eventually allows us to correct the outgoing wavefront to be flat at the sail front, at the sail, I should say. So all of this work was described in a publication, the citation for which is shown in the bottom right. But the focus here is really on this step number 3, which is doing the measurement, the phase measurement from the beacon satellites, and synthesizing a phase correction for the emitter apertures. Now, this is all the more complicated because we have power asymmetry in this system. We have a lot of power going out towards the sail, and we have a little power coming in from the beacon. And so there's this mismatch in signal strength that we can see on the ground. We're going to have any spurious reflections from our outgoing fields dominate any kind of signal that we get from our beacon. And so what we need to do is separate these two fields spectrally. So we're using multiple wavelengths, but then given the length scales involved, you've got a ground to space link, multiple wavelengths will experience significantly different dispersion. And so what the challenge is this synthesize word here in this statement. Synthesizing the phase for the emitter signal is actually a non-trivial challenge, and that's what we're trying to do in our digital signal processing at a high speed so we can actually do feedback and correction for it. So to start off, the best place to start is with a toy system, and the toy system that we're working with is the simplest case of 2 apertures. And so we have our 2 wavelength beacon here, 2 wavelengths required for doing this correction. We'll see that down the bottom of the slide. And both of these apertures receive that beacon light, which has now passed through some atmosphere. The light captured by both of these emitters are combined onto a single photodetector, and the interference of those with respect to a local oscillator is what we're measuring. So I've abstracted out a lot of the auxiliary components which make up this system. The full diagrams are available in the paper, but sufficient to say we have light going out from the OPA seed, and we have local oscillators that are matched to those beacon wavelengths used for coherent detection. Now, from this, we can determine the phase at the emission wavelength, phi e here in the bottom equation, from the phase shifts measured B1 for the first beacon wavelength and B2 for the second beacon wavelength. The capital lambdas here are the synthetic wavelengths between here B1 and B2, the 2 beacon wavelengths, and on the denominator, the emission wavelength and B1. So this gray box here is what we can measure and calculate. We also have this additional term down on the right, and this is dependent on the integer number of wavelengths passed by beacon 1 and beacon 2. And this integer number of wavelengths is effectively representing the phase accrued across this ground to space link. And the ratio now of these synthetic wavelengths determines that dispersion I was talking about before, arising from having multiple wavelengths in the system. So this term cannot really be measured in an easy way on the ground without some a priori knowledge of the length scale, of the length being interrogated. And for this reason, we treat this as an unmeasurable error. So we're trying to get as much information out of this as possible, and by controlling the ratio of these synthetic wavelengths, trying to null out the effect of this error term. So that's the principle of how we do this. Let's then talk about how we actually try to simulate this in real time on an FPGA system for being able to do this in an experiment further down the road. So I've highlighted 4 things that we kind of need to have in place in this system. Firstly, we need to be able to synthesize the phase response of each beacon wavelength due to the path length noise it experiences as it traverses through the atmosphere. That also requires us to, on demand, be able to generate dynamic path length noise in real time. Then on the ground system, we need to be able to synthesize the heterodyne interferometer response for both of these emitters, and also the phase recovery post detection needs to be multiplexed. because we are combining these two emitters, eventually more, but for now two, on a single detector. So we need some form of multiplexing. And all of this needs to operate on timescales spanning from megahertz, which is the dynamics of laser frequency noise and phase noise, down to millihertz, which is where we're actually interested in kind of atmospheric driven path length noise and fiber length noise as well. So it's a really large time base that we're trying to simulate, and that's why this project is really focused on doing this in a hardware in loop kind of simulation. So the hardware in loop simulation, we're using a National Instruments platform. So this is the hardware there is on screen. The main thing is that it's not a particularly high performance FPGA, Kintex 7. They're a couple of generations old now. So this is not running on by any means cutting edge hardware, but it is still running in real time. And a kind of functional schematic of what's involved is shown on the right. So as I described, we have the signal generation for the two beacons. We also generate what the emitter should be seeing as well. So we're effectively generating the phase response for 3 different wavelengths. We have our performance calculation at the end. So this is where we're comparing what we're getting from our measurement and projection algorithm to kind of our truth measurement, which is the emitter. And then all of this is running on FPGA. We have the ability to send any of these signals out via DACs into the electronic domain. That's to test response of the analog front end as well. So a couple of the diagnostics of the speed of the calculation, as well as some of the main latency, is down the bottom right. So we're running at a clock of 100 megahertz. The computation, so that's this entire phase measurement through to getting the wavelength, the phase calculated at the emission wavelength. That takes 530 nanoseconds, which is in fact a bit funny because our analog front end is slower at 690 nanoseconds. For our purposes today, we're decimating that information, which is still coming in at 100 megahertz, down to 1.2 kilohertz. So we have 100 megahertz throughput. Bandwidth is shaped by filters inside this phase measurement, I should say, inside the phase measurement. That's dependent on what heterodyne beat frequency you're looking at, but typically that can be megahertz scale passbands. So we have access to that information up to several megahertz. We're just decimating it down because we don't want to save bucket loads of data for every second. The other important part of this system is how well we're able to simulate the length noise that's seen by beacon 1, beacon 2, and the emitter. And so we're able to do this down to a resolution of 32.5 picometers. That's the smallest length jump because we are working in a fixed point environment. And we also have a resolution on that, a frequency resolution of 23 millihertz. Since the last update, sorry, that was a lot of information, I realized, but since the last update, we've included several features that we were going to include. So that's one of those is the dynamic length noise injection. So this is generated real time and added to all of these measurements. We've added digital interferometric multiplexing. So this is the ability to now have effectively all the signals measured at a single photodetector as per our point design. The hardware loopback I touched on, so that's being able to route signals out and back in. And now we can also detune the frequency or wavelength of any of the wavelengths in the system. So that allows us to kind of map out how the synthetic wavelength parameter, the capital lambda, affects our measurements. And I'll get to some of those results in a little bit. But first, a little bit about the digital interferometric multiplexing. So in adding a little bit more detail to the diagram from before, what we're doing is we're using this technique, which is indigenous to ANU, called digital interferometry. This is a method using pseudo-random modulation, which is imparted by these phase modulators, which are in each of the arms of the OPA, each of the kind of the control system backbone of the OPA has provision for these phase modulators. And what they allow us to do is it allows us to put on this pseudo-random noise code and identify each of the apertures based on that pseudo-random noise code. And so that allows us in this return arm lock here, this single photodetector that measures all the light coming back through from the beacons. It allows us to distinguish each of those fields based on the unique codes that are imparted to them. Now, the way this kind of works is that you have here we've got, for example, emitter 1, emitter 2, and here's the actual interference between emitter 1 and 2. We have these pseudo-randomly modulated, each with unique codes, creating this kind of heterodyne tone that's got this square wave or pseudo-random period square wave modulated on top of it. The decoding looks for the particular delay of that PRN or PRBS sequence. And when that delay is matched, we get a strong correlation, which allows us to revert back to our standard heterodyne demodulation. And so you can see in this case, channel 1 is being correctly decoded. We can get to it, we can mix down our heterodyne frequency and extract out our phase measurement of it. Any other delay in the system or any other code that we receive does not correlate with the sequences that are the sequence for channel 1. And so that all ends up as a high frequency component following the mixdown that allows us to filter that out via low pass filtering. And so all of this can be done on FPGA in parallel. So you can extract all of the different channels that you need on the single FPGA based from a single ADC as well, coming from a single photodetector. So it's a really powerful tool, and now we've got that in our simulation as well. Finally, getting along to the measurements. The first measurement is a very straightforward one. It's where we just scan the length, and we scan the length over quite a long way. So here on the left, we have integer number of wavelengths. So this is micron scale, all the way up to a meter plus, still at the same length scale, meter plus an integer number of wavelengths. And what we've plotted here is the beacon 1 measurement. Beacon 2 is analogous but slightly shifted. And you can see that for small length scales, for micron size, all three, the beacon 1, emission, and the synthesized phase, which is coming from our algorithm, they all match up. It's all great. Once we get up to the meter scale, the beacon 1 measurement is quite significantly displaced from the emission wavelength. The synthesized phase, however, is tracking well. This is what we expect, but it's good to see. Looking a bit more closer now at the residuals, we can already see, even at the wavelength scale, length scale, the individual beacon measurements are starting to accrue a fairly significant error. This is already at 2 milliradian only after 2 wavelengths of path length noise. When we increase up to the meter scale, what we see is the beacon 1, a single beacon cannot be used. The wavelength error is too large. However, an interesting thing that we found out of the simulation work arising from the quantization noise in the system on FPGA, which it's something we didn't see in the analytics, is that we get this bounded cyclic error, which kind of evolves with increasing length, but it is still bounded, and it's bounded at the milliradian scale. So it's an error source that came out of kind of implementation, but it's an error source that we didn't actually predict just purely from the analytics of the system. So that's kind of really good information that's come out of this project that informs our design moving forward. The key thing to note here is that this bounded error is still bounded, and it's bounded at a level that's below kind of our quantum noise limit predictions. And so it's good to know about, but it's not a showstopper either.
2 minutes, Chithur.
Thank you. Moving on to laser frequency. So here now we've started to tune our different wavelengths around. So from if we null out that error term that I described before, what we get is the dark blue trace, and we see that we have a bounded error that's well below our lambda 30 design requirement. This is a plot that's going 7 orders of magnitude from micron to 10 meters length scale. And this is the length difference between the positions of 2 apertures in that array, the Z position of 2 apertures. As predicted, we start to see that error term increase as the differential length increases, only surpassing our requirement once we reach the multi-meter kind of length scale. This is really good to see because it's something that we predicted before as well, and the error kind of comes out to be roughly in the same location. So this is from our analytics from before. Now we have that on hardware as well. And kind of the last measurement I'd like to show is the long-term performance. So this is now looking at an hour timescale. The length noise that we've introduced is about 30 millimeters of path length total over the hour. And that's shown in the top right. The individual phase measurements or the errors arising from those phase measurements are shown in the bottom right. So you can see the individual beacons, the dispersion starts to make those measurements unusable. The projected signal error is still bounded around 0. Looking at the frequency domain, we can see the spectrum of the injected atmosphere that we're using, and we can see the noise shelf or the noise trace of the projected signal error. It's got this interesting hump shape, but this is that bounded cyclic error that you saw before, that sinusoidal type error with length. So expected, and it's good to see that it's well below our target stability, even over length scale, time scales, I should say, of an hour or so. Moving ahead, we're building the optics now. The DSP is effectively done. So component and subsystem characterization is underway. That's led by Noah and Paul, and we're estimating Q2 2024 first light. We have our roadmap for including integrated photonic components for Q3. So they're currently being designed by the Royal Melbourne Institute of Technology in Melbourne, Australia. And we're aiming for outdoor testing in Q1 2026. Out of this project, it's been really fruitful, and I have to thank Sonny and the team for contributing to this type of research. So we're currently in the process of finalizing our results and preparing 2 manuscripts. We initially thought 1, but the first one outlining what we've talked about today. And the second one is on some novel self-calibration methods, which kind of came out of this work. Being able to have a toy system to play around with lets you do interesting things and find out things that you can't really don't really plan for, I should say. But that's also really useful for kind of the engineering of building such a large array. And thank you all for your time.
Thank you, Chithura. Appreciate it. It's good to see all the neat stuff that you guys are up to, and how you've been able to kind of pound flat the different things you wanted to pound flat as you tried to mature what you understood about the system, trying to take it to the next level. And it's exciting to see a slide where you're talking about making that migration to actually doing some hardware tests, indoors, assuming to begin with, but getting to the outdoors as soon as you can. I wish there was something we could do to help, speed that up for you, just like we could for everybody else. So, but to whatever small degree that LSI could help through the resources it could bring to bear and the resources of our philanthropic donors, it's been our pleasure to be able to lean in with everybody. So let me pull us back out of presentation mode. And so now we've got an opportunity for some facilitated Q&A. So if folks want to turn on their cameras, and if anybody's been kind of thinking about a question they wanted to roll out, that'd be really good. I see John Bush is already at it. So,
So Adam, can you discuss the implications of the sign error?
Sure. So it's either 1 plus C or 1 minus C. And C is a correlation. So it's bounded between -1 and 1. So actually, the reason I think that this sign error was never noticed for like 60 years is that the bounds are the same, whether it's plus or minus, right? And if the correlation is a cosine, it amounts to a phase shift by pi radians, whether you have a plus or a minus there. So, unless you make the distinction between the two different correlations that I talked about, there is no consequence, right? Because Bell's inequality is still violated by both of these two different correlations. And if you look at Boole's inequality and you only use the quantum correlation, it's still violated. So you would think, well, Boole's inequality.
You said Boole's inequality is violated?
Yeah. So the only time that it matters is when you're using Boole's inequality with the negative sign, the correct sign, and you're thinking in terms of the implied correlation that I showed in the talk, which is not the one that's usually used. That's when it matters.
So are we local or non-local?
Well, I think that the result, once this is all tidied up and made precise, I think that what I am going to argue is that the conclusion based on Bell's theorem and the tests is premature, because until you can actually test the implied correlation, which means being able to have perfect control over photon sequences, you don't know. Yeah.
Gotcha. So don't know.
Yeah. I mean, I think that there's no reason to actually say that it's non-local. The main reason so far has been Bell's inequality. That's supposedly shown that it's non-local.
Mm-hmm.
But I would say that if that isn't the case, then why should we think so? Right.
Yeah, because the perspective from coming from the HQA community is we see that we don't need non-locality to capture any of these quantum effects hydrodynamically. So we see it nowhere. They seemingly see it everywhere. So it's easier to believe this sort of profound result, which follows from the Bell test. But we see no reason for it. So we're a little bit skeptical. Yeah.
Good spicy question to start us off, John. What are the kind of questions we got? Got a couple coming in from the webinar attendees from Larry. He's got two in there. One for Chithura. Why not use the sodium laser at 95 to 100 kilometers? Let's see, 100 kilometers up, used by ground-based astronomy and producing an artificial star at 589 nanometers.
Yeah, that's a good question. The short answer is that for mission concepts like Breakthrough Starshot and several others, the launch altitude is, or the orbital height is quite high, and so you can imagine a triangle. Well, it's an isoplanetic angle problem. So the atmosphere sampled by the atmospheric correction field, in this case sodium, would not sufficiently cover an array of that size pointing at an object that high. So what you end up needing is your source, your atmospheric correction source, and in our case the beacon, being effectively co-located or within the isoplanetic angle of the array and the sail. So that's why we can't use a sodium layer. It's just too low an altitude. I also see that pulse timing, time of flight. There's again, it's the distance to the sailcraft, especially once it's launched. The time of flight for any kind of return signal is just far too large for any kind of meaningful feedback or feed forward correction. So you need to be able to make measurements on the ground and make them fast.
Thank you, Chithura. I got another question for Jerry on the fusion rocket. Jerry, Larry says he notes that your plasma density is roughly 10 to the 20th per cubic meter, which is the tokamak Greenwald limit plasma instability. Is this due to the centrifugal plasma?
That particular density came out of a limit we in centrifugal confinement called the Kármán number limit, and I'll just come back to that in a second. The centrifugal mirrors have some of the same instability issues at tokamaks, but they're more susceptible to flute instabilities, and the centrifugal confinement actually is very good, at least in simulation, has been shown to suppress those. So a lot of the stability issues that might be relevant in a tokamak are not as relevant in a centrifugal mirror confinement. Now, that said, where we end up finding limits, we just can't cram as many reactants in there as we would like. The ultimate limit is your azimuthal velocity cannot exceed the alphanic speed. If you do that, then you start distorting the magnetic field excessively, and that obviously leads to problems. So as much as I would like to crank up the number density above 110 to the 20 and get a higher power density, I really am kind of limited by that alphanic speed number. Does that help?
Unfortunately, he can't use the microphone right
okay.
now. I think you gave a pretty good answer. If he's got some more questions, he can type them in. Shaka, did any questions come in on YouTube? You think we need to throw up into the sandbox?
I don't think so. The questions that I see would have been answered by just watching a few minutes longer.
Okay. All right. Very good. Very good. So some more questions from the panelists before I take chair prerogative.
Yeah, it looks like Phil has a question.
Phil, your hand's raised?
Yeah. That's actually a question for Jeremy. So when I think about the issue of photon production from basically varying boundary conditions, it's going to fall sort of into two pieces. One, if I take an electron and I accelerate it or just oscillate it, You know, I'm in effect kind of changing boundary conditions in some unusual way, and I get photon production, which is obviously very, very common. So that's maybe one way to get very efficient photon production, is do something very, very simple like that. But the problem is, of course, that, and I think this may be true generically, is that you're going to have to inject energy into the system in order to get the photon production. So I'm wondering whether this is any different than having a flashlight on board, effectively. In other words, you need to have a power source for the flashlight. So I don't know, can you kind of maybe address that more generally?
Phil,
Sure,
I'm gonna embellish what you just said for the folks listening. What's the newtons per kilowatt? Is this any better than a laser pointer?
Yeah, so I think so I definitely agree that you always have to put in energy for any of these sorts of systems. So you're not getting energy for nothing, right? So it's basically just a matter of how you convert that energy. And so this would be basically a form of mechanical energy into photon energy in the case of like a dynamic Casimir effect. And in the case of flashlight or laser pointer, yeah, you'd be doing chemical energy into photon energy. And so then I guess, yeah, maybe a question does come down to the efficiencies of those processes. And I think the efficiency of the conversion through quantum fluctuations could in principle be higher. And I'm not sure what the limit is. And that's kind of an open question. I think that's interesting. Is how efficiently can you do that process? The loss mechanisms are basically the generated photons. So from that point of view, it could be highly efficient. Vacuum friction could be another issue, but that's actually usually much smaller. So I think it does come down to an efficiency question, which is an open one. But yeah, you definitely have to put energy in to get energy out.
So if I could just pick one thing, I think I heard there's a small potential for the newtons per kilowatt to be potentially better than a laser pointer, but it's still to be determined.
Yeah, that's what I think. Yeah.
Okay. All right. Gotcha. What other kind of questions we got from the panelists? And for the attendees, you get questions, type them in. If you want to, it's too long to type, just, let us know you want to be bumped up to a panelist. We'll bump you up to a panelist as well. No worries. All right, I'm gonna take chairman's prerogative here. So Jeremy, I'm gonna continue to pick on you for a minute. In your mind, what do you think would be the cost of an experiment if you were to go to the NSF or something like that? Right? Have you given any thought to a ballpark to get to actually spinning one of those little dumbbells that you were showing for? I think that's probably the Purdue dumbbell, right? And
right,
having it made of different materials. What does it cost for that?
Yeah, that's a good question. So, I mean, in principle, that type of experiment is not terribly expensive because you basically are using kind of an inverted microscope, a little vacuum chamber, and some lasers. So that's a relatively low-cost experiment. I think that the tricky part is seeing how you can get to higher rotational speeds, which I think is really what you need to have a measurable amount of photon generation. But that's definitely something that we're thinking about. And that's kind of like some of the next steps we wanted to consider from like we have kind of the other extreme. We've considered a very idealized case that gives a very high rate. So what is maybe the experimental limitations given current material systems? I think that's the next question. But I think that such experiments would be quite reasonably priced. Things that you could accomplish under those sorts of scales of projects, kind of small scale NSF as opposed to like big center projects. Yeah.
Okay, perfect. Well, that's great. Thank you for qualifying that. That was good.
Sure.
Phil, I'm going to switch to you. Unless anybody else has a question, throw your hand up or something. I'm going to go with a couple I had written down. Phil, so you and I have had discussions over the years about demo opportunities. And I remember from your talk, you were talking about you guys are making like a couple of these laser sources per week. In your mind, is there any way for you to, if you were to stay in this slow in pennywise kind of mode to get to the point where you could potentially do like a demo to Dragon or something like that? Like, say Dragon does a mission to station, and whenever it undocks and comes home, there's something in the trunk or something like that of the Dragon that you could do some kind of an experiment with.
Okay, yeah. First of all, I wanted to thank Chathura for a very nice presentation you had. It was very nice. Thank you. The issue that I see here is really a question of what becomes practical in terms of demonstration programs. So for example, we're just finishing up a NASA program for lunar activities using directed energy. And that's in our mind, kind of a low-hanging fruit, and becomes very, very useful, practical, and doesn't require extremely large arrays. In the mode that we're in, we kind of, we make the sub elements, and we do about, as I mentioned, about 2 a week. But we're just, if we had many more resources, we could do, as many as you want per week. But then it becomes this question of, where do you want to go with this? If you really want to design something for a demonstration program, some of the demonstration programs we've looked at have been lunar based. There's a lot of interest in lunar activities. A lunar to Earth, Earth to lunar, lunar to cislunar. So there's a wide range of mission possibilities here, and some of them do not require extremely large arrays. The relativistic flight, like we had in our NASA programs for about a decade now, do require these very, very large arrays. So then it becomes an economics question. And I think this is part of what we pointed out for many, many years is there's a long-term roadmap here, which does make the possibility of getting to relativistic flight quite practical, but along the way there's many, many practical examples of using this. They're outlined in our many papers and now a very long book on the subject. But it does come down to this interesting question of economics. So we published a paper several years ago called The Economics of Interstellar Flight, which kind of looks at the sensitivity of the various parameter spaces of costs. And that's something you might want to take a look at if anybody's interested in where we're going in the longer term. But I think one has to be realistic here and say, proposing a relativistic mission is not a practical thing to do right now, just because of the costs. It works on paper, and so far works in laboratory, but that's a question of how much money is it going to cost. And we saw this recently, from some other private foundations that were looking at our work and concluded this is really quite expensive. It's doable, but it's very expensive. And then that was the correct conclusion, and we pointed that out from day one, that this is possible to do, but is very expensive with current technology. So then it becomes a question of how do you match those two ends of the spectrum? It can be done, but it's very expensive to do. So how much money are you willing to pay to do it? And how does the technology scale with time to make it cheaper in the future, much like our consumer level electronics? And this is something where I do feel it's worth a very, very sage discussion, particularly realizing that it's not all or nothing here, is that many of the missions that we've proposed, such as starting by sending a small spacecraft to Mars faster than chemical propulsion can achieve, are not incredibly expensive. They don't break the bank of, $100 billion kind of mission. And in today's dollars, just to remind people, Apollo would be $300 billion. So people that think you can do this for cheap, I think haven't really thought completely through the whole issue. But there are lots of missions, and the lunar case is a good one, where we built something in the lab and it's, could be put on the moon now, where it solves a problem that you want to solve, and it's pretty cheap to solve that problem. It doesn't solve a problem of getting spacecraft, to Alpha Centauri region, but it does solve practical problems. And that we feel is the only path forward here is to provide people solutions to problems they have. And in the process, you work your way along this roadmap to eventually reaching relativistic flight.
Right.
I don't know if that helps answer. We've always looked at this in a very holistic way, and trying to be, reasonable about it, not promising we can, say for $1 billion, get to the nearest stars. I just don't see that right now.
Right. Provide some more near-term practical, decompose the technology and help it solve problems that we have today. So
correct. Yeah, give people what they need, and they will pay you to solve the problems they need to solve.
yeah, and by doing that, you get closer to maybe one day being able to do the other.
Yeah, exactly.
I think I've got a good question from Larry, but Larry, I'm going to pop you up to a panelist in your questions for Jeremy. Hold on a second here. I'll promote you to panelist. Or Larry, you may need to take some action on your side.
Okay, can you hear me?
Yeah, we got you. Larry, you there?
Yeah, I'm here. Can you hear me?
Yes.
Okay, this is for Jeremy. I'm really intrigued by what you're doing with the dynamic Casimir effect, and one of the things is to try to determine whether or not it's real. Let's put it that way. And then, given that it's real, what is the efficiency in photon production? And I just call to your attention single bubble sonoluminescence was characterized by Julian Schwinger not long before he passed away as being an example of dynamic Casimir effect. And others have measured the collapse of those to be less than a picosecond long. It has a non-black body radiation output, which is, it turns out we measured, it's down in the soft X-rays, but we've also measured gamma rays coming out of these. So the set of experiments we're planning on doing, I hope in the next year, you've kind of given me a clue as to some things I should be looking at, in particular, counting the number of photons we come out in addition to knowing what their energy characterization is. But have you given any thought to that as a way of measuring the output from dynamic Casimir forces?
You mean looking at the photon spectrum or the photoluminescence?
Well, in particular, the photon spectrum that you see.
Yeah. Good question. So with the dynamic Casimir effect, there's a well-characterized photon spectrum that you should also see for that. And it's been worked out for certain cases. So, for example, like with the oscillating plates, and you can see that the spectra is related to the oscillation frequency. It kind of peaks at the oscillation frequency and decays from there. But there is a spectrum associated with that, and we're exploring that as well for these rotational objects. So I think it'll be interesting when you start putting in the actual dielectric materials and the various material resonances and how that affects the spectra as well. But yeah, I think that's exactly what you'd want to do rather than just only counting photons. Also looking at the spectrum of them would be a good signature to describe if that is the effect or if it's something else.
Yeah, well, in particular, what I like about the idea of counting those photons and knowing what the spectrum is, you can now, as you say, discount several different theories. Are these simply thermal effects?
Right. Yeah. Good thoughts.
So I'm gonna finish with the last question for the day. I know we're a little long, but we had so many good talks with tidbits that just didn't want to cut anybody off if we didn't have to. So I think each talk went just a little long, but that's okay. That just provides a lot more good and technical goodness that everybody was probably tuning in for. So this question is for Jerry Carson. When you were going through the efficiency of your system for, I think it was for deuterium helium-3, it looked like the curve was asymptoting about 50%. Is that correct?
Yeah, and that actually was for deuterium tritium system. For a DHE3 system, that would be a bit higher.
Okay, that was going to be my question, and because I know Hall thrusters can start to close in on the upper 50% efficiency, so I just didn't know what kind of knobs you could turn, right? So deuterium helium-3 can actually be better than 50%.
Yeah, and the issues with those is you have several factors that work sometimes together and sometimes against each other. But that curve in particular was extracted from data on a DT system. And I got the question, why were they grouped so closely, and went back and derived an efficiency equation. And for that system, they obviously fell along pretty well, but the DHE3 system would be a slightly higher, particularly if we were using like an ammonia or water propellant where you had some heavier species in there.
Okay. Gotcha. Okay, I think we've had a great day today. Thanks everybody online that joined us. Thanks for everybody that joined us in the Zoom webinar, and thanks again to all the performers. I really do appreciate all your hard work and everything you've done. If you would stick around just a second, I'm going to go ahead and start shutting down the different broadcast things, and we'll have just a small minute or two internally. So thank you everybody on YouTube. We're about to bring down the stream. Thank you for attending.
Thank you.
Okay, the